The observable universe stretches an astonishing 93 billion light-years across, a cosmic expanse so vast that every point of light we see in the night sky is just a grain of sand on an endless beach of galaxies. Within this immeasurable arena of time and space, there are an estimated 2 trillion galaxies, each teeming with billions, sometimes trillions, of stars. From our tiny perch on a small blue planet orbiting an ordinary star, we peer into this infinite canvas and witness the echoes of creation itself. The light that reaches us from the most distant galaxies began its journey over 13 billion years ago, when the first cosmic structures were still forming in the darkness after the Big Bang. In this vastness, we find every type of galaxy imaginable. Spirals spinning like celestial pinwheels, immense elliptical giants glowing with ancient light, and chaotic irregulars shaped by violent collisions. As we embark on this journey through the observable universe, we will travel from the familiar spirals of our own galactic home to the faintest whispers of light at the universe's edge, tracing the grand story of matter, motion, and cosmic evolution written across the stars. Our voyage through the galaxies begins right here in the familiar glow of our own cosmic home. The Milky Way galaxy. To the naked eye, it appears as a faint milky band stretching across the night sky, but through the lens of science, that soft glow transforms into something magnificent. A colossal spiral galaxy, spanning over 100,000 light-years in diameter and containing more than 400 billion stars, along with vast clouds of gas, dust, and an invisible halo of dark matter that extends far beyond what we can see. The Milky Way is not just our address in the cosmos. It is a living, breathing structure of motion, gravity, and creation, a galactic ecosystem sustained by the forces that have governed the universe since time began. At its heart lies a dense, luminous central bulge, a sphere of tightly packed ancient stars orbiting a mysterious gravitational anchor. The supermassive black hole Sagittarius A. This monstrous object, about 4 million times the mass of our Sun, sits quietly in the galactic core, its immense gravity shaping the orbits of stars within a few light-years. Around this bulge, the Milky Way unfurls into a majestic disk of spiral arms, grand sweeping structures where stars are born from collapsing molecular clouds. These arms are not solid bands of stars, but rather waves of density moving through the disk like ripples on water. Within them, new suns ignite, illuminating the darkness and filling the galaxy with brilliant blue-white light. Our solar system resides in a relatively calm region called the Orion Arm, or the Orion Spur, a minor branch located between two of the Milky Way's major arms, the Sagittarius and Perseus arms. From here, we orbit the galactic center at a staggering 828,000 kilometers per hour, completing a single revolution every 230 million years. To put that in perspective, since the dinosaurs roamed the Earth, our planet has only made a single full trip around the Milky Way's core. It's a humbling reminder that we are not merely part of space. We are participants in its eternal motion. If we could view our galaxy from above, we'd see it as a barred spiral, with a central bar-shaped structure of stars uncutting through its core, a common feature among spiral galaxies. The Milky Way's bar channels gas inward, feeding both star formation and the growth of the central black hole. Extending outward, the spiral arms glow with youthful brilliance, rich in H2 regions, where clouds of hydrogen are ionized by newly born stars. Nebulae like the Orion Nebula, the Eagle Nebula, and the Carina Nebula serve as some of the most spectacular examples of this ongoing galactic artistry. Meanwhile, in the outer reaches of the disk, older, redder stars mark regions where star formation has slowed, creating a gentle gradient from youthful blue to ancient amber as one moves outward from the core. Surrounding the galactic disk is the halo, a roughly spherical region filled with ancient metal-poor stars and globular clusters, tightly bound stellar families that predate most of the Milky Way itself. The halo is also where the invisible influence of dark matter becomes apparent. Though we cannot see it, we know it must exist because the stars in the Milky Way's outer regions orbit far faster than they should if only visible matter were present. This dark matter halo acts as a gravitational scaffold, holding the galaxy together against the centrifugal force of its rotation. Without it, our galaxy, and indeed all galaxies, would simply fly apart. But even as grand as the Milky Way is, it is merely a small node in a much larger cosmic web. Our galaxy is part of a galactic family known as the Local Group, a gravitationally bound collection of more than 50 galaxies stretching across roughly 10 million light-years. Within this group, the Milky Way is one of the two dominant members, the other being the Andromeda Galaxy, M31, a slightly larger spiral that mirrors our own structure. The Triangulum Galaxy, M33, is the third largest member, while the rest are smaller dwarf galaxies, like the Large and Small Magellanic Clouds, which orbit the Milky Way like celestial satellites. The Magellanic Clouds, visible to the naked eye from the southern hemisphere, are irregular dwarf galaxies filled with young stars and nebulae. They serve as living laboratories for studying how galaxies form and evolve under gravitational influence. These companions are constantly being pulled and stretched by the Milky Way's gravity, their gas and stars forming delicate tidal bridges that hint at an ongoing exchange of matter. It's a reminder that galaxies are not static islands. They are dynamic, interacting systems, locked in a perpetual gravitational dance that shapes their destiny. Zooming out further, the Milky Way and Andromeda are not only neighbors, they are future partners in a cosmic collision. Astronomers have determined that in about 4.5 billion years, the two galaxies will merge, drawn together by mutual gravity. When that happens, their stars will weave together in a colossal ballet spanning millions of years. Most stars, including our Sun, will pass through unscathed. The spaces between them are vast. But their orbits will shift, and the night sky will transform dramatically. The collision will ignite new waves of star formation as clouds of gas compress, and over billions of years, the two spirals will settle into a single elliptical galaxy, sometimes referred to as Milkometa. This event, both violent and beautiful, is a natural part of galactic evolution, a process repeated countless times across the cosmos. And while this may seem extraordinary, it's anything but rare. The Milky Way is just one of hundreds of billions of galaxies in the observable universe, each with its own history of collisions, mergers, and rebirths. Some are younger, teeming with bright blue stars and swirling nebulae. Others are ancient, filled with the faded light of stars long past their prime. Together they form the intricate structure of the universe, clusters and filaments stretching for unimaginable distances, bound together by the unseen gravity of dark matter. Our cosmic neighborhood is the perfect prelude to a much larger journey, one that takes us beyond our local group into the greater realm of superclusters, where galaxies gather by the thousands, connected through the vast architecture of the cosmic web. Beyond the Milky Way's spiral arms lies an endless expanse of galactic communities. The next stop in our voyage through the universe's grand design, our journey now drifts beyond the comforting spiral of the Milky Way, out into the vast intergalactic sea that surrounds it, a realm known as the Local Group. Here, gravity binds together more than 50 galaxies in a loose but unmistakable gravitational embrace, forming our immediate cosmic neighborhood. It's a collection of galaxies that, though separated by millions of light years, are connected through the invisible threads of gravity, tugging, pulling, and shaping each other in an endless silent ballet that has lasted for billions of years and will continue for billions more. The Local Group spans roughly 10 million light-years across, and though it is but a minuscule fragment of the observable universe, it represents the intricate web of interactions that define the cosmic order on every scale. At the center of this group are three major players: the Milky Way, the Andromeda Galaxy, M31, and the Triangulum Galaxy, M33. These three spiral galaxies dominate the gravitational dynamics of the Local Group, while dozens of smaller dwarf galaxies orbit them like moons around planets. The Milky Way and Andromeda are roughly equal in mass, each containing hundreds of billions of stars, while Triangulum, smaller and more delicate, acts almost as a bridge between them. Its gravitational relationship with both giants still a subject of deep astronomical study. Together they form a gravitational triangle that holds the Local Group in balance. The Andromeda Galaxy, located about 2.5 million light-years from us, is the nearest large spiral galaxy and the most massive member of the local group. It is a majestic spiral, larger than the Milky Way by perhaps 20 to 30%, with a brilliant central bulge and sweeping arms alive with the light of countless suns. Andromeda is moving toward us at roughly 110 kilometers per second, pulled closer by the same force that binds all galaxies in the group, gravity. Despite the vast gulf of space between us, our destinies are already intertwined. The Milky Way and Andromeda are locked on a collision course, one that will reshape both galaxies in about 4.5 billion years. When these two galactic titans meet, it will not be a cataclysmic explosion, as one might imagine when hearing the word collision. Instead, it will be a graceful interweaving, a slow-motion waltz that unfolds over hundreds of millions of years. Because stars are separated by enormous distances, far greater than their own diameters. They will mostly pass by one another without direct impact, but the gravitational tides produced by this encounter will be extraordinary. They will stretch and warp both galaxies, pulling out tidal tails of stars and data that arc across the scale like celestial ribbons. Clouds of interstellar gas will collide, compress, and ignite bursts of star formation, turning dark patches of space into radiant nurseries filled with newborn suns. Over time, the two spirals will lose their distinctive arms and merge into a single massive elliptical galaxy, glowing with the light of ancient stars. A new entity born from the fusion of two great cosmic families. Even as the Milky Way and Andromeda prepare for this future embrace, they are already surrounded by smaller companions that orbit like satellites in a gravitational web. The large and small Magellanic Clouds, irregular dwarf galaxies visible from the southern hemisphere, are among the most famous. They are currently interacting with the Milky Way, leaving behind trails of hydrogen gas known as the Magellanic Stream, a structure that stretches across more than 600,000 light-years of space. Other companions include Sagittarius Dwarf Galaxy, Canis Major Dwarf, and Draco, each slowly being torn apart by the Milky Way's tidal forces, their stars added to our galaxy's growing halo. These faint, ghostly galaxies are reminders that even giants like the Milky Way are built from cosmic cannibalism, slowly consuming smaller galaxies over time to grow in mass and complexity. Andromeda has its own entourage, more than 30 known dwarf galaxies, including M32 and M110, two elliptical companions orbiting close to its spiral disk. These small galaxies have been heavily shaped by Andromeda's gravity. Some have been stripped of their outer layers of stars and gas, while others are in the process of being drawn in completely. The gravitational relationships among these members are not static. They are constantly shifting, evolving, and merging. Astronomers studying the local group have even suggested that Triangulum, M33, might be a distant satellite of Andromeda, possibly orbiting it in a slow looping path. If so, the eventual Milky Way-Andromeda merger may one day draw Triangulum into the mix as well, creating a three-way galactic union that will dominate this region of space for the remainder of cosmic time. Beyond these well-known names, the local group is filled with hidden galaxies, many of them faint and diffuse, detectable only through deep surveys. Some are so small that they contain only a few million stars, yet they are crucial to understanding how larger galaxies like ours formed. These dwarfs are thought to be the building blocks of the early universe, relics from an epoch when matter first began clumping together under gravity. The local group provides astronomers with a cosmic laboratory, a way to observe galactic evolution in our own cosmic backyard. By studying how these galaxies move, interact, and merge, we uncover the same fundamental processes that shape the universe on scales far beyond our reach. What holds all of this together is a shared center of mass, a gravitational midpoint located somewhere between the Milky Way and Andromeda. Around this invisible point, every galaxy in the local group orbits in slow motion. Over billions of years, this gravitational harmony will evolve into something far simpler. A single massive elliptical galaxy surrounded by the faint remnants of its former satellites. As time passes, the local group will eventually drift toward the Virgo supercluster, drawn by the gravitational pull of even larger cosmic structures. The local group, as mighty as it seems, is just a tiny node in the vast web of the universe. As we leave this local congregation of galaxies behind, our path carries us outward to the Virgo supercluster, a realm where thousands of galaxies congregate in vast gravitational cities of light. Beyond the quiet intimacy of our local group lies the bustling architecture of the universe itself, where clusters collide, black holes reign, and the large-scale structure of the cosmos begins to reveal its breathtaking design. Drifting beyond the bounds of the local group, we enter a grander cosmic stage, a domain where galaxies are no longer isolated islands, but members of a vast continental congregations. This is the Virgo supercluster, a colossal assembly of galaxies, stretching over 110 million light-years across, containing not thousands but tens of thousands of galaxies, arranged in colossal filaments and clusters. The Virgo supercluster is not just another region of space, it is the gravitational basin that our local group belongs to, our cosmic address within the universe's immense architecture. When we gaze outward toward the constellation of Virgo, we are looking directly into the heart of this enormous structure, a realm of unimaginable scale and power. At the center of this supercluster lies the Virgo cluster, an immense gathering of more than 2,000 galaxies, located roughly 54 million light-years away. Here, gravity weaves galaxies together into a densely packed swarm, held by a shared gravitational center dominated by massive ellipticals and surrounded by spirals, lenticulars, and irregulars. The Virgo cluster represents a critical node in the cosmic web, a crossroads where filaments of galaxies converge, forming one of the most massive gravitational structures in our cosmic vicinity. Within this gravitational metropolis, galaxies are constantly interacting, colliding, and reshaping one another in a ballet that plays out across millions of light-years. The cluster's most prominent members are M87, Messier 87, M49, and M60, each a gargantuan elliptical galaxy containing trillions of stars. M87 stands out as one of the most remarkable galaxies ever observed. It is a supergiant elliptical galaxy, the central anchor of the Virgo cluster, and one of the most massive known. Spanning over 120,000 light-years, M87 radiates an almost golden light, produced by countless old stars that populate its dense core. Yet what lies at its center is even more astonishing. A supermassive black hole with a mass of about 6.5 billion suns. This is the same black hole that the Event Horizon Telescope imaged in 2019, the first direct image ever captured of a black hole's shadow. That orange-hued ring of light glowing against the blackness of space was not only a triumph of astronomy, but a window into the gravitational heart of a galaxy, proof that these cosmic monsters anchor and influence entire galactic systems. Around M87, smaller galaxies swarm in orbits defined by the cluster's collective gravity. Many are dwarf ellipticals or lenticular galaxies, stripped of their gas and dust through the fierce environmental effects of the cluster. The Virgo cluster is a harsh place for galaxies. As they fall inward, they pass through a superheated intra-cluster medium, a thin but incredibly hot plasma that fills the space between galaxies, glowing in X-rays. This medium can strip galaxies of their gas in a process called ram pressure stripping, effectively shutting down star formation and transforming once spiral galaxies into dead ellipticals. In this way, clusters like Virgo are engines of galactic evolution, recycling matter and energy in cycles that span billions of years. What makes the Virgo cluster so essential to our understanding of the cosmos is its role as a template for the large-scale structure of the universe. Astronomers have long observed that galaxies are not randomly distributed through space, they form hierarchical systems. Small galaxies cluster around larger ones, those groups gather into clusters, and clusters themselves are drawn together into even larger assemblies known as superclusters. The Virgo supercluster is part of an even greater structure called the Laniakea supercluster, which spans over 500 million light-years and contains an estimated 100,000 galaxies. Laniakea, meaning immense heaven in Hawaiian, is the gravitational domain within which the Milky Way, Andromeda, and all our neighboring galaxies reside. Every galaxy within this colossal region flows, slowly and majestically, toward a central gravitational basin known as the Great Attractor, an area dense with matter, both visible and dark. When we examine the Virgo supercluster in detail, we see that it is not a single uniform blob of galaxies, but rather a web of filaments and subclusters. These cosmic filaments are the highways of the universe, colossal threads of dark matter and galaxies stretching for hundreds of millions of light years, connecting clusters like Virgo, Coma, and Fornax into a grand cosmic lattice. Between these filaments lie vast cosmic voids, regions almost completely empty of galaxies, where the density of matter is far below average. These immense voids are not just gaps, they are the silent counterpart to the filaments, the yin to the cosmos's yang, shaping the gravitational landscape of the universe. Within the Virgo cluster itself, the dynamics are intricate and mesmerizing. Some galaxies are moving at speeds exceeding 1,000 kilometers per second, their paths bent by the gravitational pull of their neighbors. When they collide, the results are spectacular. Starbursts, tidal streams, and galactic mergers are common sights here, each a step in the cosmic cycle of death and rebirth. The cluster also hosts active galactic nuclei, AGN, galaxies whose central black holes are voraciously feeding, releasing torrents of radiation and energetic jets that pierce intergalactic space. M87's iconic jet, extending over 5,000 light-years, is one such phenomenon. A colossal stream of particles moving near light speed, powered by the rotation and magnetic fields around its black hole. These jets shape their environments, injecting energy into the surrounding gas and influencing how stars form across millions of light-years. What's extraordinary about the Virgo supercluster is not only its scale, but also its role in anchoring our cosmic neighborhood. The local group, home to the Milky Way and Andromeda, sits on the outskirts of this vast structure, connected to it by long filaments of galaxies and dark matter. Over time, measured in billions of years, our local group will slowly drift toward Virgo's center, pulled by the gravity of its immense mass. One day, far in the future, our galaxy and others in our vicinity may become part of the Virgo cluster itself, merging into a single gravitational domain. In this sense, the Virgo supercluster represents not just a snapshot of cosmic structure, but a glimpse into our galactic destiny. From the perspective of cosmic architecture, the Virgo supercluster exemplifies the hierarchical nature of the universe. How matter, born from the tiny quantum ripples in the early universe, grew through gravity and into galaxies, clusters, and superclusters. These enormous cosmic structures are the skeleton of the cosmos, built on a foundation of dark matter and shaped by the mysterious force of dark energy, which drives the expansion of space. When we observe the Virgo cluster, we're not just seeing a collection of galaxies. We're looking at a fundamental building block of the universe, a visible node in a structure that spans billions of light years. And yet, even here, among thousands of galaxies bound in an immense gravitational city, we are still only beginning to glimpse the larger cosmic web that extends beyond, a structure so vast and interconnected that it defies imagination. The Virgo supercluster, magnificent as it is but one strand in that infinite tapestry, one glowing thread woven into the universe's grand design. As we move outward from this colossal assembly, we begin to see how galaxies, clusters, and superclusters link together, forming the cosmic web, a structure that reveals the true architecture of everything that exists. As we venture farther outward from the Virgo supercluster, the universe begins to reveal its most astonishing and fundamental pattern, a structure so vast and intricate that it has been poetically called the cosmic web. When astronomers first mapped the large-scale distribution of galaxies using deep sky surveys and redshift measurements, they discovered something unexpected. Galaxies are not scattered haphazardly through space like random grains of sand. Instead, they form immense filaments and walls, colossal tendrils of matter that stretch for hundreds of millions of light years, weaving together a structure that spans the observable universe. Between these filaments lie vast cosmic voids, enormous, nearly empty regions of space where very few galaxies exist. Together, the filaments, walls, and voids form the grand architecture of the cosmos, a three-dimensional lattice of unimaginable scale and beauty. At its heart, the cosmic web is the result of gravity sculpting the universe over billions of years. After the Big Bang, matter in the universe was not evenly distributed. Tiny fluctuations, quantum ripples in the infant cosmos, created regions that were ever so slightly denser than their surroundings. Over cosmic time, gravity amplified those small differences, pulling matter together to form clumps that eventually became galaxies, clusters, and superclusters. Meanwhile, the less dense regions between them expanded faster, becoming the great voids that now make up much of the universe's volume. This interplay of gravity and expansion gave rise to the intricate network we now see in large-scale cosmological maps, a structure that spans tens of billions of light-years and yet traces its origins to the very first moments after time began. When seen in large-scale simulations, such as those produced by the Millennium Simulation or the Illustris and TNG projects, the universe looks almost organic. Filaments of galaxies wind and twist like neural pathways in a cosmic brain, connecting nodes where galaxy clusters reside. These filaments are rivers of matter, composed not only of galaxies and gas, but also vast quantities of dark matter, the invisible substance that makes up most of the universe's mass. Though dark matter cannot be seen directly, its gravitational influence is unmistakable. It acts as the scaffolding upon which galaxies form, shaping the web's structure and guiding the motion of ordinary matter like a hidden hand. Within this web, the nodes, where multiple filaments intersect, are the locations of the largest galaxy clusters in the universe. The Virgo cluster, Coma cluster, and Perseus cluster are all examples of these gravitational crossroads, where thousands of galaxies gather in cosmic metropolises. Between these nodes stretch the filaments, sometimes hundreds of millions of light-years long and tens of millions wide, populated by galaxy groups, star-forming systems, and intergalactic gas that glows faintly in X-rays and ultraviolet light. These filaments form the highways of cosmic evolution, channeling matter from the voids into the clusters and fueling the growth of galaxies along their paths. The regions between these luminous threads, the cosmic voids, are equally fascinating. Voids can span tens to hundreds of millions of light-years and contain only a few galaxies scattered sparsely through their emptiness. The largest known voids, like the Boötes void, measure over 300 million light-years across, making them some of the most desolate expanses in existence. Yet even these seemingly empty regions are not truly void. They contain a thin mist of dark matter, intergalactic gas, and radiation, the faint remnants of the universe's earliest structures. If the filaments are the bones of the universe, the voids are its lungs, vast expanses through which cosmic expansion breathes. The cosmic web is not static, it is alive with motion. Over billions of years, galaxies migrate slowly along the filaments, pulled by the gravity of clusters at the intersections. This flow of matter is sometimes described as a cosmic river, streaming toward gravitational centers in a process known as hierarchical structure formation. Small galaxies and clusters merge to form larger ones, and as they do, the filaments themselves become thicker and more pronounced. This grand cosmic motion continues even now. Every galaxy, including our own Milky Way, is participating in this universal migration, slowly drifting through the web toward regions of greater density. Recent advances in astronomical observation have allowed scientists to map the cosmic web in unprecedented detail. Surveys like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Spectroscopic Instrument, DESI, have charted millions of galaxies, revealing the three-dimensional distribution of matter across billions of light-years. These maps show vast structures with poetic names: the Great Wall, the Hercules Corona Borealis Great Wall, the CFA2 Great Wall, and the Sloan Great Wall, titanic sheets of galaxies stretching across cosmic space. The Hercules Corona Borealis Great Wall, for instance, is estimated to be 10 billion light-years long, making it one of the largest structures ever discovered. Yet even this may be only one strand among many, hinting that the universe's full structure might be beyond what we can observe. The cosmic web also plays a critical role in how galaxies form and evolve. The environment of a galaxy, whether it lies deep within a cluster, along a filament, or isolated in a void, profoundly influences its shape, color, and behavior. Galaxies in dense regions tend to be older, redder, and elliptical, having exhausted their gas through interactions and mergers. Those in filaments often show intermediate characteristics, while galaxies adrift in voids are typically smaller, bluer, and rich in gas. Cosmic survivors that have evolved undisturbed for billions of years. In this way, the web determines not just where galaxies exist, but what kind of galaxies they become. Dark matter and dark energy together govern the long-term evolution of this vast structure. Dark matter provides the gravitational scaffolding, pulling galaxies into filaments and clusters. Dark energy, by contrast, drives the universe's accelerated expansion, stretching the web and widening the voids. The tension between these two forces, one pulling, the other pushing, shapes the cosmos on the grandest scale. In the far future, as expansion continues to accelerate, many of the filaments may thin and detach, isolating galaxy clusters into lonely islands amid an ever-darkening sea. The cosmic web, once tightly connected, will slowly unravel, leaving behind the faint traces of its former grandeur. From a human perspective, the scale of this structure is almost beyond comprehension. The cosmic web encompasses everything. Every star, planet, and atom that has ever existed. It is the blueprint of creation, the framework upon which the universe's story unfolds. To trace its strands is to read the history of time itself. From the first fluctuations in the cosmic microwave background to the galaxies shining billions of years later. And yet, despite its enormity, it remains elegant and unified, a pattern that mirrors the delicate complexity of life itself. Our place within this web is humble but profound. The Milky Way, along with its neighbors in the local group, resides on one of these vast filaments that connect to the Virgo supercluster, a single glowing strand among trillions. Every direction we look, the web stretches on, revealing that we are not the center of the universe, but a thread in its infinite tapestry. From this realization arises a deep cosmic perspective, that even in our smallness, we are part of something incomprehensibly grand, a universe woven together by gravity, matter, and time. As we continue our journey through this cosmic structure, our path now leads us deeper into the galaxies themselves, to the dazzling spirals of light and color that populate the filaments of the web. These galaxies, the luminous jewels of the cosmos, are where the true artistry of creation unfolds. From their swirling arms to their blazing cores, we will explore the spirals of creation, the magnificent star-forming galaxies that illuminate the universe. Now, as we step along the glittering filaments of the cosmic web, our gaze turns to the most captivating and architecturally elegant creations in the universe. Spiral galaxies. These are the true masterpieces of cosmic design, the celestial pinwheels that dominate our imaginations when we think of galaxies. With their sweeping arms of starlight, interwoven with lanes of dust and atom, spiral galaxies embody both the grace and the dynamism of the cosmos. They are the cradles of creation, where stars are born and live and die in a continuous cycle that has persisted for billions of years. And yet behind their beauty lies a complex and delicate balance of gravity, motion, and time. Spiral galaxies account for roughly 60 to 70% of all galaxies in the local universe, and they are defined by their distinctive disk-like structure. At their heart lies a galactic bulge, a dense spherical region of older stars surrounding a central supermassive black hole. From this bulge extend the spiral arms, graceful curving structures that wind outward through the galactic disk. These arms are not solid objects, rather they are density waves, regions of higher concentration that move through the galaxy, compressing gas and dust as they pass. As this material is compressed, it triggers the birth of new stars, which then light up the arms in brilliant shades of blue and white. This is why spiral galaxies are so radiant. They are galactic nurseries, constantly forming new stars from the vast reservoirs of interstellar matter that course through their disks. The Milky Way, our home galaxy, is itself a magnificent spiral. More specifically, a barred spiral galaxy. Its central bar funnels material toward the core, fueling both star formation and the activity of its supermassive black hole, Sagittarius A. The Milky Way's spiral arms, such as the Perseus arm, Sagittarius arm, and our own Orion spur, are filled with sprawling nebulae where stars are being born even now. The Orion Nebula, the Eagle Nebula, and the Carina Nebula are but a few of the stellar nurseries scattered along these arms, where new suns ignite in glowing clouds of hydrogen and dust. As we orbit the galactic center at over 800,000 kilometers per hour, we are carried along one of these spiral pathways, part of a structure that rotates majestically once every 230 million years. A single galactic year. Beyond our galaxy, countless spirals paint the sky with their luminous symmetry. Among the most famous is Andromeda, M31. Our closest spiral neighbor, visible to the naked eye from dark skies as a faint smudge of light. At over 220,000 light-years across, Andromeda is larger than the Milky Way and contains roughly 1 trillion stars. Its spiral arms are strikingly defined, filled with clusters of young, hot stars and dark dust lanes that trace the flow of interstellar matter. In many ways, Andromeda is a mirror of our own galaxy, a twin whose destiny is intertwined with ours, as the two are set to merge billions of years from now in a slow but spectacular galactic union. Another jewel among the spirals is the Whirlpool Galaxy, M51, perhaps the most iconic spiral galaxy ever observed. Located about 31 million light-years away in the constellation Cons Venatici, it is a textbook example of a grand design spiral galaxy, with two perfectly symmetrical arms winding outward from a bright central core. The Whirlpool owes much of its beauty to its smaller companion galaxy, NGC 5195, which is gravitationally interacting with it. This cosmic dance has stirred up waves of gas and dust, triggering intense bursts of star formation along the arms. The bright blue regions that give the galaxy its characteristic glow. Through telescopes, M51 looks almost alive, as if the universe itself were painting in motion. Then there is the Pinwheel Galaxy, M101, a sprawling spiral in the constellation Ursa Major, some 21 million light-years away. M101 is enormous, about 170,000 light-years in diameter, and its arms are rich in star-forming regions, supernova remnants, and clusters of massive young blue stars. The Pinwheel Galaxy is notable not only for its size and beauty, but also for the clarity with which its structure can be observed. High-resolution images from the Hubble Space Telescope reveal the delicate interplay of light and dust, showing that even within a single arm, the forces of gravity, rotation, and starbirth weave a dynamic tapestry of cosmic life. The structure of spiral galaxies owes its form to the intricate physics of angular momentum and gravitational balance. When gas clouds collapsed in the early universe, even the slightest rotation was amplified as the material contracted, just as an ice skater spins faster when drawing in their arms. This conservation of angular momentum caused many forming galaxies to flatten into rotating disks, setting the stage for the creation of spirals. The spiral arms themselves arise from density wave theory, a concept introduced in the 1960s by C.C. Lin and Frank Hsu. They propose that the arms are regions where stars and NEM temporarily pile up as they orbit the galactic center, similar to how cars slow and bunch up in a traffic jam. As the wave moves on, new stars form behind it, creating the illusion of a fixed spiral pattern even though the individual stars continue to move independently. The interplay of color in these galaxies reveals their life cycles. The arms, where new stars form, glow blue and white due to the intense heat of young massive stars. The central bulge, by contrast, shines with a warmer golden light, the collective glow of older, redder stars that have long since exhausted their hydrogen fuel. This visual contrast tells the story of cosmic evolution, the restless youth of the spiral arms, and the mature calm of the galactic center coexisting in one elegant structure. In addition to their luminous splendor, spiral galaxies are engines of chemical enrichment. Every generation of stars forges heavier elements through nuclear fusion, carbon, oxygen, silicon, iron, which are then dispersed into the interstellar medium when stars die, particularly in supernova explosions. This recycled material becomes the raw fuel for new stars and planets. Thus, the spiral arms are not only factories of starlight, but also furnaces of creation, where the very elements of life are forged and scattered through space. Rotation gives spiral galaxies their dynamic grace, but it also poses a profound mystery. When astronomers measured the rotation curves of spiral galaxies, how fast stars orbit at different distances from the center, they discovered something astonishing. The outer regions of galaxies rotate far faster than expected, based on visible matter alone. The only explanation is the presence of an unseen mass, dark matter. This invisible halo surrounds the galaxy, extending well beyond its luminous disk and providing the extra gravity needed to hold it together. Without dark matter, the stars in the outer arms would fly off into space, and the beautiful spiral patterns we admire would not exist. Spiral galaxies are not eternal. Over billions of years, as they consume their gas and interact with other galaxies, they evolve into different forms. Collisions and mergers can transform them into elliptical galaxies, and star formation gradually slows as their interstellar gas is depleted. Yet even in this transformation, they leave behind structures, stellar streams, tidal bridges, and remnant cores that bear witness to their spiral origins. From the Milky Way to Andromeda, from the whirlpool to the pinwheel, spiral galaxies remind us that the universe is both orderly and alive, filled with motion and change. Each arm, each cluster, each luminous swirl is a record of time, a snapshot of the ongoing cycle of birth and renewal that defines the cosmos. To gaze upon a spiral galaxy is to witness the very process of creation, frozen in light millions of years old, spiraling eternally through the darkness. But spirals are only part of the story. For every galaxy that glows with the restless light of new stars, there are others, vast, ancient, and serene, that have long since completed their youthful phase. As we move forward, we leave behind the bright blue arms of the spirals and journey into the realm of elliptical galaxies, the great red giants of the universe, whose quiet luminosity tells the tale of cosmic maturity and time's enduring passage. As we drift farther along the vast threads of the cosmic web, the energetic glow of the spiral galaxies begins to fade. The brilliant blue arms of youth give way to a calmer, warmer light. The subdued radiance of elliptical galaxies, the giants of the universe. These galaxies are the elder statesmen of the cosmos, immense, ancient, and dignified, their forms shaped not by graceful rotation, but by the chaotic history of cosmic mergers. Unlike the lively dynamic spirals teeming with newborn stars, elliptical galaxies are monuments to time itself. Vast spheres are ellipsoids of old stars, silent and stable, basking in the amber glow of their collective age. Elliptical galaxies make up roughly 20% of all galaxies in the observable universe, but they account for a disproportionate share of stellar mass. They are the heavyweights of the cosmos, some stretching over 1 million light-years in diameter and containing trillions of stars. Where spiral galaxies are thin and disc-shaped, ellipticals are smooth, rounded, and nearly featureless, with little or no internal structure. They range from small dwarf ellipticals, barely larger than globular clusters, to the gargantuan CD galaxies found at the centers of massive clusters. The true leviathans of the galactic world. The defining characteristic of ellipticals is their stellar population. They are dominated by old, low-mass stars that shine with a soft reddish light, a stark contrast to the blue-white brilliance of spirals. The lack of young, hot stars tells us that these galaxies have long since ceased star formation. Their vast reservoirs of gas, the raw material for creating new stars, were either used up billions of years ago or stripped away by gravitational interactions and energetic feedback from supermassive black holes. What remains is a population of mature stars, aging gracefully as they drift through the galaxy in random orbits. This randomness of motion is one of the hallmarks of ellipticals. In spirals, stars move in orderly rotation around the galactic center, giving rise to their elegant arms. But in ellipticals, stars move in all directions, their orbits more like those in a swarm than a spinning disk. The result is a smooth spheroidal shape, a cosmic equilibrium achieved after countless gravitational encounters. Many of these galaxies formed through galactic mergers, collisions between spirals and other galaxies that scrambled their structure and dissipated the gas needed for further starbirth. In that sense, ellipticals are the end products of galactic evolution, the quiet remnants left behind after the violent fireworks of earlier epochs. Among the greatest of these is Messier 87, M87, the central galaxy of the Virgo cluster. A true cosmic titan. M87 spans over 120,000 light-years, and its mass is estimated to exceed 3 trillion solar masses. It is a supergiant elliptical, a behemoth surrounded by a vast halo of globular clusters and dark matter. But what truly sets M87 apart is what lies at its heart, a supermassive black hole roughly 6.5 billion times the mass of the Sun. This is the same black hole whose shadow was captured in the first ever direct image of a black hole by the Event Horizon Telescope in 2019. The image revealed a glowing ring of light, the Event Horizon silhouette against the surrounding accretion disks, confirming one of the most profound predictions of Einstein's general relativity. That glowing halo was more than a scientific milestone. It was a window into the soul of an elliptical galaxy. The black hole at M87's core powers an enormous relativistic jet, a stream of charged particles that blasts out from the galaxy's nucleus at nearly the speed of light. This jet stretches for more than 5,000 light-years, cutting through space like a cosmic spear, visible even in an optical and radio wavelengths. It is one of the clearest demonstrations of how supermassive black holes, once thought to be passive monsters, can profoundly shape their host galaxies. In M87, the energy released by the black hole helps regulate the flow of gas throughout the galaxy, preventing new stars from forming and maintaining the elliptical's characteristic quiescence. Other examples of elliptical galaxies display similar majesty. NGC 4889, located in the Coma cluster, is another supergiant elliptical with a central black hole thought to exceed 20 billion solar masses, one of the largest known. Closer to home, Centaurus A, NGC 5128, is a peculiar elliptical with remnants of a spiral galaxy still visible within it, the scars of a recent merger. These galaxies, though lacking the delicate spirals of younger systems, possess a grandeur all their own, an austere beauty born of age and scale, a reminder that the universe's most impressive creations are not always its most active. The light from elliptical galaxies is rich in red and yellow hues, a direct consequence of their aging stellar populations. The absence of blue stars, which burn hot and die young, reveals that the last major wave of star formation occurred many billions of years ago. In their early youth, these galaxies were likely turbulent and luminous, their gas-rich environments producing stars at a furious rate. But as they evolved, their gas was consumed or expelled, and the galaxies transitioned into quiet maturity. Today, they shine not with the exuberance of creation, but with the quiet persistence of endurance. The slow, steady glow of a billion suns nearing the end of their lives. Despite their apparent stillness, elliptical galaxies remain dynamically complex. They are surrounded by extended halos of dark matter, hot gas, and globular clusters, some containing like tens of thousands of these ancient stellar systems. X-ray observations reveal that the spaces between stars are filled with hot plasma, heated to tens of millions of degrees, emitting a faint but detectable glow. This gas is often enriched with elements like iron, oxygen, and silicon, the ashes of countless supernovae that exploded long ago. Thus, even in their silence, ellipticals are repositories of cosmic history, preserving the heavy elements that future generations of stars and planets may one day inherit. The contrast between ellipticals and spirals represents the dual nature of the universe: creation and completion, birth and endurance. Spirals are the vibrant children of the cosmos, constantly renewing themselves through star formation, while ellipticals are the ancient sages, embodying the long, slow evolution that follows. Yet both are bound by the same physical laws and cosmic forces. Indeed, many of today's elliptical galaxies were once spirals, transformed through collisions that stripped away their youth and left behind their mature, rounded forms. In a broader sense, elliptical galaxies serve as reminders of the universe's inevitable aging. Just as stars exhaust their fuel and fade into darkness, galaxies too evolve from brilliance to quietude. The ellipticals we see today are the cosmic fossils of a more active era, their light reaching us from a time when the universe was half its current age. Their silence is not emptiness, but the echo of 1 billion stellar lives, their glow a lingering testament to creation's enduring legacy. And yet, not all galaxies follow this serene path. Some defy order entirely. Small, chaotic, and irregular in shape, they drift through the universe like cosmic remnants of past collisions. These are the irregular and dwarf galaxies, the scattered fragments of galactic evolution, still shaping and being shaped by the gravity of larger systems. As we move onward, we descend from the grand serenity of ellipticals into the chaotic beauty of the irregulars, where disorder reigns and the early conditions of the universe still echo in miniature. As we journey out deeper through the cosmic landscape, the smooth symmetry of the elliptical galaxies and the elegant grace of the spirals begin to fragment into something more chaotic, more primal. Here, at the smaller scales of galactic evolution, we encounter the irregular and dwarf galaxies, the cosmic outliers. They are the misfits of the galactic family, galaxies without the defined arms of spirals or the stately roundness of ellipticals. Yet within their asymmetry lies a powerful truth. These small, distorted galaxies are the building blocks of the universe, the raw material from which larger galaxies are forged, and the survivors of cosmic events that have reshaped the heavens for billions of years. Irregular galaxies are, by definition, those that lack any coherent structure. They are often asymmetrical, distorted, and fragmentary, shaped by gravitational interactions with their larger neighbors or by the aftermath of past collisions. While their appearance may seem haphazard, these galaxies represent some of the most dynamic environments in the cosmos. Their gas-rich compositions and turbulent conditions make them breeding grounds for intense star formation, sometimes even more vigorous than that found in well-ordered spirals. Unlike the mature calm of ellipticals or the organized rhythm of spirals, irregulars embody cosmic chaos, the untamed side of galactic evolution where gravity, time, and chance still compete for dominance. A striking example of this chaos can be found in the Large and Small Magellanic Clouds, two irregular dwarf galaxies that orbit our own Milky Way. To the naked eye, they appear as faint, misty patches in the southern night sky, but through telescopes they reveal sprawling, star-forming regions and distorted shapes, the direct result of gravitational forces exerted by the Milky Way. The Large Magellanic Cloud, LMC, located about 163,000 light-years away, is home to the spectacular Tarantula Nebula, one of the most active star-forming regions in the local group. Within it lies R136, a cluster containing some of the most massive and luminous stars known. The Small Magellanic Cloud, SMC, though smaller and fainter, is no less fascinating. Its stars and gas are stretched by tidal forces, leaving trails of matter that connect it to the LMC. Together, these two galaxies are engaged in a gravitational dance that is slowly funneling their gas toward the Milky Way, a process that may eventually lead to their complete absorption into our galaxy. Irregular galaxies like the Magellanic Clouds illustrate a key principle of cosmic evolution. Small galaxies build big ones. In the early universe, before grand spirals and massive ellipticals existed, it was tiny protogalactic fragments, early dwarf galaxies, that began to merge under gravity to form larger systems. This process, known as hierarchical merging, continues to this day. The Milky Way itself bears evidence of this ongoing growth. Astronomers have discovered stellar streams, long, faint trails of stars stretching across our galaxy's halo. These streams are the remnants of dwarf galaxies that have been torn apart by tidal forces, their stars slowly assimilated into the Milky Way's structure. In essence, every massive galaxy is a mosaic of countless smaller ancestors, their individual identities lost in the grand synthesis of cosmic time. Beyond our galactic neighborhood, irregulars take on a variety of forms and personalities. Some, like NGC 1427A in the Fornax cluster, are galaxies in transition, warped by the gravitational pull of nearby giants. Others, like IC10 in the local group, are bursting with young, massive stars and glowing fiercely with the light of recent starbirth. Many irregulars are dwarf galaxies, systems containing only a few million to a few billion stars, a mere fraction of the hundreds of billions that populate galaxies like the Milky Way. Yet, despite their modest size, they play an outsized role in cosmic evolution. Their high gas content and frequent interactions make them crucial catalysts for star formation and galactic growth. One of the most intriguing kinds of irregular galaxies are the blue compact dwarfs, BCDS, small intensely luminous galaxies undergoing explosive starburst activity. These galaxies, such as Zwicky 18 and Hanise 2-10, are often seen as windows into the early universe, as their primitive chemical compositions resemble those of galaxies shortly after the Big Bang. They contain low levels of heavy elements, meaning they have experienced few cycles of star formation, and their young, hot stars bathe the galaxy in a brilliant blue light. Observing these galaxies allows astronomers to study the conditions that prevailed during the epoch of galaxy formation when the first stars and stellar clusters began to illuminate the darkness. Then there are the tidal dwarfs, galaxies born not from the primordial clouds of the early universe, but from the debris of galactic collisions. When two large galaxies interact, their mutual gravity can fling out long tails of gas and stars, which can collapse to form new, smaller galaxies. These tidal dwarfs are, in a sense, recycled galaxies, second-generation systems created from the remnants of older ones. Unlike most other galaxies, tidal dwarfs are often deficient in dark matter, since the material that forms them comes primarily from the outer regions of galactic disks, where dark matter density is lower. They serve as vivid evidence that galaxy formation is an ongoing creative process, not a single event confined to the early universe. Dwarf galaxies, despite their diminutive size, are the most numerous type of galaxy in the universe. For every large spiral or elliptical, there may be hundreds or thousands of dwarfs orbiting nearby or floating alone in intergalactic space. Some are ultra-faint dwarfs so dim that they are nearly invisible, detectable only through their gravitational effects or the subtle light of a few hundred stars. Others, known as dwarf spheroidals, have little gas and are populated by ancient stars, resembling miniaturized versions of elliptical galaxies. These small galaxies are key laboratories for studying dark matter, as their motions often suggest a greater presence of unseen mass compared to visible stars, sometimes hundreds or even thousands of times more. Irregular and dwarf galaxies also act as chronicles of cosmic history. Because their gravitational environments are relatively simple compared to massive galaxies, they often preserve clues about the early stages of galaxy formation. Their chemical compositions reveal the nucleosynthetic footprints of the first generations of stars, while their star clusters and variable stars serve as cosmic timekeepers, allowing astronomers to trace back billions of years of galactic evolution. Studying them is like examining the fossils of the universe, fragile, scattered pieces that together reconstruct the story of cosmic growth and change. In their apparent disorder, these galaxies remind us that chaos is an essential ingredient of creation. Their irregular shapes, their collisions and mergers, their bursts of star formation, all of these processes contribute to the ongoing cycle that builds the larger, more structured galaxies we see today. Without the irregulars and dwarfs, the universe would lack its diversity, its texture, its continuous renewal. Every massive spiral and elliptical galaxy is, in truth, the sum of countless irregular ancestors, each one a vital chapter in the grand narrative of cosmic evolution. Yet, for all their formative power, these small galaxies are often victims of the same forces that create them. As they drift too close to larger galaxies, they are stretched, torn, and ultimately consumed, their stars scattered like cosmic ashes into the halos of their massive companions. It is a violent but necessary process, one that fuels the growth of the universe's great structures. But sometimes the violence doesn't end with consumption. When galaxies of all sizes collide, the result is one of the most spectacular phenomena in all of astronomy: galactic mergers. These cosmic encounters are not mere collisions, but symphonies of gravity, birthing stars, reshaping galaxies, and giving rise to entirely new forms. As we continue our journey through the galactic zoo, we will witness the awe-inspiring spectacle of galactic collisions and mergers. the cosmic dance that has sculpted the universe from chaos into beauty. When galaxies collide, the universe itself seems to come alive. The calm, stately motion of billions of stars gives way to a cosmic ballet of unimaginable scale. A slow-motion dance choreographed by gravity lasting hundreds of millions of years. These are galactic collisions and mergers, the most spectacular and transformative events in the cosmic story. Though the word collision suggests destruction, the reality is far more elegant and complex. Because the distances between individual stars are so vast, galaxies pass through one another like ghosts, their stars rarely colliding directly. Yet their gravitational fields interact profoundly, reshaping each other's structures, triggering massive waves of star formation, and eventually fusing into entirely new galactic forms. Galactic collisions are an essential part of cosmic evolution. In the early universe, when galaxies were smaller and closer together, these encounters were far more frequent. Over billions of years, such interactions have built up the large galaxies we see today. Every massive elliptical, every sprawling spiral owes its existence in part to this gravitational artistry. The process may take eons, but the result is profound. Galaxies are reborn through their collisions, transformed into the new shapes, new sizes, and new dynamical states. The light from these encounters carries the story of the universe's creative violence, a story written not in destruction, but in transformation. One of the most iconic examples of this cosmic drama is the Antennae Galaxies, NGC 4038 and NGC 4039. Located about 60 million light-years away in the constellation Corvus. These two spiral galaxies are currently in the throes of merging, their mutual gravity pulling out long, curving tidal tails of stars, gas, and dust that stretch for tens of thousands of light-years into space. These delicate tails, which give the pair their antennae appearance, are sculpted by gravitational tides as the galaxies twist around each other. Within the overlapping regions of their disks, vast clouds of gas are compressed, igniting bursts of star formation, regions so luminous that they outshine entire galaxies. The Antennae Galaxies are among the most studied merger systems in the sky, providing a vivid snapshot of the tumultuous process that will one day shape our own galactic future. During a collision, gravity acts like a sculptor. As galaxies approach, tidal forces stretch and distort their shapes, pulling streams of stars and gas outward yet while drawing other material inward toward their cores. These tidal interactions can induce massive inflows of gas, feeding both central starbursts and supermassive black holes. In this way, collisions not only build galaxies but also fuel the engines of their centers, igniting quasars and active galactic nuclei, AGN, that can blaze with the energy of trillions of suns. The violent mixing of gas leads to turbulence, shockwaves, and compression, all of which accelerate the collapse of molecular clouds and trigger intense, short-lived bursts of star formation. The newborn stars that result from these bursts often form in clusters, some containing tens of thousands of stars. Many of these clusters will not survive for long. Gravitational interactions will tear them apart. But the most massive ones can persist for billions of years, eventually becoming globular clusters orbiting the merged galaxy. Thus, even as collisions disrupt the old order, they also plant the seeds of future structure, recycling matter into new generations of stars. Over time, the chaos settles. After their first close encounter, galaxies may swing apart for millions of years before gravity pulls them together again. Each pass strips away more material, gradually dissipating their ordered motion. Eventually, their disks lose their distinct spiral shapes, merging into a single, more spherical system, often an elliptical galaxy. In these final stages, the residual gas is consumed or blown away by stellar winds and black hole activity, halting star formation. What remains is a smooth, golden-hued remnant, a galaxy reborn in the aftermath of gravitational union. The Milky Way itself is not immune to this cosmic fate. In about 4.5 billion years, it will collide with the Andromeda Galaxy, M31. Astronomers have simulated this event in stunning detail, revealing what our skies might look like during the merger. At first, Andromeda will grow larger and brighter in the night sky, its spiral arms stretching across the heavens. As the two galaxies approach, their stars will mingle, creating vast tidal bridges and loops of light. The Sun, along with its planets, will likely be flung into a new orbit far from its current position, though the odds of a direct collision with another star remain infinitesimally small. Over billions of years, the two galaxies will merge into a single, massive elliptical galaxy, a new system sometimes called Milky Way. The process will reshape the entire local group, forming one unified, ancient giant drifting through intergalactic space. Other spectacular mergers are scattered throughout the cosmos, each telling its own version of the same ancient tale. The Mice Galaxies, NGC 4676, located about 290 million light-years away in the Coma Cluster, display long, slender tails extending for hundreds of thousands of light-years, the result of their ongoing collision. The Tadpole Galaxy, UGC 10214, with its single, graceful tail of young blue star clusters, captures another stage of this grand process. The Cartwheel Galaxy, a ring galaxy formed by a smaller companion plunging through a larger disk, shows what happens when collisions occur not head-on, but with incredible precision. Each of these systems is a snapshot in time, a frozen frame in the universal movie of creation and change. Despite their grandeur, galactic mergers are not mere spectacles. They are cosmic engines of evolution. Through them, galaxies grow in mass, mix their stellar populations, and redistribute their gas and dust. They also play a crucial role in shaping the morphological diversity of galaxies. Many of the elliptical galaxies we see today, including giants like M87, are thought to be the products of countless past mergers. Even spirals like the Milky Way have likely undergone smaller mergers, absorbing dwarf galaxies and companions over billions of years. Every galactic form, from the most orderly to the most chaotic, carries the imprint of these gravitational encounters. In the aftermath of collisions, supermassive black holes at the centers of the merging galaxies are also drawn together. Over time, they spiral inward, releasing gravitational waves, ripples in space-time, as they coalesce into a single, even more massive black hole. These events are among the most powerful in the universe, sending vibrations through the very fabric of reality. The Laser Interferometer Space Antenna, JAVEZ LISA, an upcoming space mission, aims to detect these low-frequency gravitational waves, allowing astronomers to witness the final union of galaxies, not through light, but through the trembling of space-time itself. As magnificent as they are, these galactic mergers remind us that the universe is in a constant state of renewal. What seems like destruction is, in truth, a creative act, the universe reassembling itself at ever larger scales. The stars continue to burn, the elements continue to fuse, and from the remnants of the old, new galaxies are born. But behind these visible processes lies something unseen, a cosmic framework that dictates how galaxies move, gather, and merge. This hidden structure, made of something that does not emit or reflect light, shapes the destiny of every star and galaxy in existence. It is the dark matter scaffold, the invisible backbone of the universe. As our journey continues, we will step beyond the visible and explore how this mysterious, unseen substance holds the cosmos together, guiding every collision, every spiral, and every galaxy in the grand cosmic design. Beyond the shining arms of spirals and the radiant cores of ellipticals lies a universe shaped not by light, but by shadow. A domain governed by something we cannot see, touch, or detect directly, yet whose presence defines the structure of everything. This is the realm of dark matter, the invisible scaffold upon which the cosmos is built. If galaxies are the ornaments of the universe, then dark matter is the frame that holds them in place. An unseen architecture stretching across billions of light years, binding galaxies, clusters, and filaments into the vast cosmic web we have come to know. It does not shine or reflect, it does not emit radiation, and yet without it, the universe as we see it could not exist. Astronomers first suspected dark matter's existence not because they saw it, but because of what they didn't see. In the early 20th century, Swiss astronomer Fritz Zwicky observed the Coma Cluster, a collection of thousands of galaxies. When he measured their speeds, he found that they were moving far too fast to be held together by the gravity of the visible matter alone. According to Newtonian physics, such a cluster should have flown apart long ago, yet it hadn't. Zwicky proposed that there must be dunkel materie, dark matter, providing the additional gravity needed to hold the cluster together. His calculations suggested that this unseen matter outweighed the visible matter by a staggering factor of 10 or more. Decades later, in the 1970s, astronomer Vera Rubin provided definitive evidence closer to home. Studying the rotation curves of spiral galaxies, measurements of how fast stars orbit at different distances from their centers, she made a remarkable discovery. Instead of slowing down as expected with distance, the stars in the outer regions of galaxies moved at constant speeds, as though there were an enormous amount of unseen mass surrounding them. This invisible mass, extending well beyond the luminous disk, could only be explained by the presence of a dark matter halo, a vast spherical cloud of invisible material enveloping each galaxy. Rubin's work revealed that dark matter was not merely a curiosity of clusters, but a fundamental component of every galaxy in the universe. Today we know that dark matter makes up about 27% of the universe's total mass energy content, while ordinary matter, everything that makes up stars, planets, and us, accounts for less than 5%. The rest is dark energy, the mysterious force driving the universe's accelerated expansion. This means that the very matter we can see, from glowing stars to swirling nebulae, represents only a small fraction of what truly exists. The rest, unseen and enigmatic, forms the cosmic skeleton that dictates the behavior and distribution of all visible structures. But if dark matter doesn't emit or absorb light, how do we know it's there? The answer lies in its gravitational influence. We infer its existence through the motions of galaxies, the bending of light, and the formation of large-scale structures. One of the most striking demonstrations of dark matter's presence comes from gravitational lensing, a phenomenon predicted by Einstein's general relativity. Massive objects warp space-time, bending the path of light that passes near them. When astronomers observe clusters of galaxies, they often see background galaxies distorted into arcs and rings, a clear sign of massive gravitational fields. By mapping these distortions, scientists can calculate the distribution of mass in the cluster, and in doing so, they find that most of the mass is invisible. The visible galaxies contribute only a small fraction. The rest is dark matter. One of the most famous gravitational lensing cases is the Bullet Cluster, a pair of colliding galaxy clusters located about 3.8 billion light-years away. In this system, astronomers used X-ray telescopes to observe the hot gas, the visible matter, produced during the collision. The gas clouds, which contain most of the normal matter, were slowed down by the collision and now lag behind the cluster's centers. But when scientists mapped the total gravitational mass through lensing, they found that most of it was located ahead of the gas, aligned with the galaxies instead. This indicates that the unseen dark matter passed through the collision largely unaffected, behaving differently from normal matter. The Bullet Cluster thus serves as direct visual proof that dark matter and ordinary matter are distinct, that the invisible outweighs the visible many times over. Dark matter's role in the universe extends far beyond individual galaxies and clusters. It is the architect of the cosmic web itself. In the aftermath of the Big Bang, dark matter was the first ingredient to begin collapsing under gravity, forming vast invisible halos and filaments long before ordinary matter could cool and form stars. These dark matter halos acted as gravitational wells, pulling in gas that eventually cooled, condensed, and gave birth to galaxies. In this sense, galaxies are like raindrops forming in invisible clouds, luminous condensations within a framework of unseen substance. The universe's entire large-scale structure, its filaments, walls, and voids, traces the distribution of dark matter, revealing an intricate pattern that underlies all of cosmic evolution. Even though we understand its gravitational effects, the true nature of dark matter remains one of the greatest mysteries in modern physics. It does not interact with light or electromagnetic forces, and it passes through normal matter almost entirely undisturbed. Scientists believe it is composed of non-baryonic particles, something fundamentally different from protons, neutrons, and electrons. Among the leading candidates are WIMPs, weakly interacting massive particles, hypothetical particles that could interact via the weak nuclear force, and axions, ultralight particles that might subtly influence the polarization of light. Despite decades of searching, no direct detection has yet been made, though massive underground detectors like Xenon NT, Lux Zoi PLEN, and Super CDMS continue to listen for the faintest whispers of interaction. Meanwhile, alternative theories such as modified Newtonian dynamics, MOND, and extensions of general relativity attempt to explain galaxy motions without invoking dark matter, by altering the laws of gravity at large scales. Yet while these theories can explain certain galactic behaviors, they fail to account for phenomena like the bullet cluster or the detailed patterns in the cosmic microwave background radiation, both of which align perfectly with models that include dark matter. The evidence for dark matter is everywhere, woven into the very structure of the cosmos. When we look at the cosmic microwave background, CMB, the afterglow of the Big Bang, we see faint ripples in temperature that reflect the density fluctuations of the early universe. These patterns, mapped in exquisite detail by satellites like Planck and WMAP, match predictions that include a significant dark matter component. Without it, the universe would have expanded differently, and galaxies as we know them might never have formed. Dark matter's invisible hand has guided the universe's evolution from the very beginning, shaping every cluster, every filament, and every star that now shines in the night sky. And yet, for all we have learned, we remain like shadow watchers in Plato's cave, seeing only the effects, never the thing itself. Dark matter challenges our deepest understanding of physics, forcing us to confront the limits of human perception. It reminds us that most of reality may be hidden from view, existing beyond the narrow band of light to which our eyes are tuned. Still, where darkness gathers, so too does mystery deepen. For if dark matter is the scaffolding that holds galaxies together, then at their very centers lurks another invisible force, one that bends not only light and space but time itself. Our next step takes us into these gravitational abysses, where even light cannot escape. The supermassive black holes that reside in the hearts of galaxies, shaping their evolution from within. At the center of nearly every massive galaxy lies an abyss, a place where gravity grows so intense that not even light can escape. These are the supermassive black holes, the hearts of darkness that govern the inner lives of galaxies. They are both destroyers and creators, paradoxical engines of order that influence the motion of stars, the flow of gas, and even the birth of new suns. Though invisible, their presence shapes galaxies across cosmic time. They are the anchors of the luminous spirals and ellipticals we see, silent hidden monarchs around which entire star systems revolve. A supermassive black hole typically contains anywhere from a few million to tens of billions of times the mass of our Sun, compressed into a region no larger than our solar system. Unlike their smaller stellar mass cousins, which form from collapsing stars, these giants are thought to have grown over billions of years through the accretion of gum and the merger of smaller black holes. Their origin remains one of the universe's greatest mysteries. Did they begin as the remnants of the first generation of massive stars? Or did they form directly from the collapse of enormous clouds of primordial gas in the early universe? Whatever their birth story, their existence is now seen as inseparable from that of their host galaxies. At the core of our own Milky Way, about 27,000 light-years from Earth, lies one such behemoth, Sagittarius A, pronounced A star. With a mass of roughly 4.3 million suns, it sits quietly in the galactic center, surrounded by a swirling cluster of stars that orbit it at tremendous speeds. For decades, astronomers tracked these stars with high precision using infrared telescopes, watching them complete elliptical paths that trace the invisible hand of gravity itself. The most famous of these, known as S2, swoops within just 17 light hours of the black hole at speeds exceeding 25 million kilometers per hour. From these orbits, scientists were able to calculate the exact mass of Sagittarius A, confirming beyond doubt that it was indeed a supermassive black hole. In 2022, the Event Horizon Telescope collaboration released the first ever image of its shadow, a glowing ring of light surrounding a dark core, providing humanity with an unprecedented glimpse into the heart of our galaxy. But while Sagittarius A is relatively quiet, not all supermassive black holes are so restrained. In some galaxies, these titans are voraciously feeding, consuming matter from their surroundings in a spectacular process that releases more energy than entire galaxies emit from their stars. As gas and the dust spiral inward, they form an accretion disk, a rotating structure that heats up through friction to extreme temperatures, glowing across the electromagnetic spectrum. Near the black hole's event horizon, magnetic fields twist and channel particles into relativistic jets, beams of energy that shoot out into space at nearly the speed of light. When we observe such phenomena from across the universe, we see them as quasars, the blazing, hyperactive cores of distant galaxies, so bright they can outshine the combined light of hundreds of billions of stars. The term quasar, short for quasi-stellar radio source, was coined in the 1960s when astronomers first detected mysterious objects emitting intense radio waves yet appearing star-like in optical telescopes. It was later discovered that these were not stars at all, but galactic nuclei powered by supermassive black holes. Quasars represent the most energetic phase of galaxy evolution, often occurring when galaxies are young and rich in gas. During this stage, the central black hole feasts on matter at an extraordinary rate, converting gravitational energy into light with an efficiency unmatched by any other known process. Some quasars are so distant that their light has traveled for more than 13 billion years, allowing us to peer back into the dawn of time and witness black holes already billions of solar masses large, even when the universe was less than a billion years old. Among the most famous of these is 3C273, located in the constellation Virgo. Discovered in 1963, it was the first quasar ever identified, and its brightness and distance revolutionized our understanding of the universe. Though 3C273 is more than 2.4 billion light-years away, it is visible through even modest telescopes, shining with a brilliance that defies comprehension. Its light emanates from an accretion disk so hot it glows in ultraviolet and X-ray wavelengths, while a jet of relativistic particles extends for hundreds of thousands of light-years into intergalactic space. Observations of quasars like 3C273 demonstrated that black holes are not passive voids, but engines of cosmic energy, capable of shaping their galaxies and influencing their environments across vast distances. The influence of these cosmic engines extends far beyond their immediate surroundings. When a supermassive black hole feeds, the radiation and outflows it generates can heat and expel gas from the galaxy, suppressing further star formation. This process, known as AGN feedback, plays a crucial role in galactic evolution. It regulates how fast galaxies grow, preventing them from becoming too massive too quickly. In this way, black holes act as cosmic thermostats, balancing the creation of stars with the energy they themselves release. Without them, galaxies might overproduce stars and collapse under their own gravitational weight. Paradoxically, the most destructive forces in the universe are also the most essential for maintaining its equilibrium. Supermassive black holes also serve as cosmic timekeepers, marking the stages of galactic life. In their youth, galaxies are active and luminous, their central black holes blazing as quasars. As the available gas is consumed or expelled, the activity diminishes, and the galaxies settle into quieter forms. Spirals are ellipticals with dormant cores. Yet even in dormancy, the black holes remain, their gravitational pull dictating the motions of nearby stars and gas. Occasionally, when a stray star wanders too close, it is torn apart in a tidal disruption event, reigniting the core in a brief but spectacular flare. A reminder that the heart of darkness never truly sleeps. The connection between galaxies and their central black holes is now understood to be profoundly symbiotic. Observations show that the mass of a galaxy's bulge is tightly correlated with the mass of its black hole, suggesting that they grow together, influencing each other through gravity, radiation, and feedback. It is as though each galaxy and its black hole are engaged in eternal dialogue. The galaxy feeding the black hole shaping the galaxy's destiny. In a sense, supermassive black holes are both the graves and wombs of creation. They mark the end of matter's journey, where light itself succumbs to gravity, yet they also drive the processes that birth new stars and regulate cosmic structure. Their paradoxical nature, invisible yet powerful, destructive yet creative, reflects the very essence of the universe. A balance between order and chaos, expansion and collapse, life and entropy. And so, from these dark hearts at the centers of galaxies, energy surges outward, igniting vast regions of space and triggering episodes of furious creation. Our next step in the journey takes us to these fiery epics of renewal, to galaxies in the throes of a starburst activity, where collisions and inflows of gas ignite cosmic fireworks on a galactic scale. In the grand evolving tapestry of the cosmos, there are moments when galaxies light up with a brilliance that defies their usual pace of creation. Brief but extraordinary episodes when they are reborn in a frenzy of star formation. These are the starburst galaxies, the blazing forges of the universe where matter transforms into light at an almost unimaginable rate. Like a heartbeat that suddenly quickens, these galaxies experience a surge of energy and vitality, creating thousands of new stars every year, a rate hundreds of times greater than that of a typical spiral like our Milky Way. And though these cosmic fireworks burn briefly on the timescale of the universe, their effects echo for billions of years, forever changing the structure, color, and destiny of their host galaxies. A starburst galaxy is defined not merely by its beauty, but by its intensity. In these galaxies, vast reserves of gas, the raw material of stars, collapse under gravity and ignite nearly all at once, forming massive clusters of hot, luminous young stars. The ultraviolet light from these newborn giants ionizes the surrounding gas, creating spectacular emission nebulae that glow like embers in a cosmic forge. These regions shine so brightly that they can outshine the rest of their galaxy, radiating across the electromagnetic spectrum. From infrared, where dust re-radiates absorbed energy, to the ultraviolet and X-ray wavelengths produced by massive, short-lived stars and supernovae. What triggers these galactic infernos? The most common culprits are collisions and mergers. When galaxies interact gravitationally, their gas clouds are compressed, forcing material toward the galactic center. This compression acts as a cosmic spark, igniting star formation on a massive scale. Sometimes even a close encounter without a full merger is enough to induce a starburst, as the gravitational theta stir up the interstellar medium and funnel gas inward. These collisions are not destructive in the way we might imagine. They are creative upheavals, moments when galaxies shed their old forms and give birth to new generations of stars, clusters, and planetary systems. One of the most famous examples is M82, the Cigar Galaxy, located about 12 million light-years away in the constellation Ursa Major. Once a relatively ordinary galaxy, M82 is transformed into a starburst powerhouse after a close encounter with its neighbor M81. The gravitational tug from M81 triggered massive inflows of gas toward M82's core, where it now fuels one of the most intense star-forming regions in the nearby universe. In the galaxy's central kiloparsec, stars are forming at a rate nearly 10 times that of the Milky Way's entire disk. The energy released by these newborn stars drives super winds, colossal outflows of hot gas that erupt from the galactic center, visible as red filaments stretching tens of thousands of light-years into intergalactic space. These winds carry heavy elements, the ashes of dying stars, into the surrounding void, enriching the intergalactic medium with the seeds of future worlds. Another spectacular example is the antennae galaxies, which we've already encountered in their merging embrace. Their collision has not only distorted their shapes, but it has also sparked multiple starburst regions, each containing thousands of stellar nurseries. The sheer density of star formation in these regions is so high that it rivals the conditions believed to have existed in the early universe. Similarly, the NGC 4038/4039 system's infrared glow betrays the presence of countless young, dusty star clusters, evidence that galaxies, in their most chaotic moments, can also be at their most creative. Starburst activity is not limited to colliding systems. In some galaxies, internal processes, like the formation of a bar structure, can drive gas toward the center. where it accumulates and triggers starbursts. These galaxies often show bright, compact nuclei and ring-like formations where the inflowing gas settles and ignites. Examples include NGC 253, the Sculptor Galaxy, and NGC 6946, the Fireworks Galaxy, both of which exhibit dense central regions glowing with newly formed stars. In the Fireworks Galaxy, supernovae are so frequent that astronomers have observed more than 10 in the last century alone, a staggering rate that gives the galaxy its name. The timescales of starbursts are fleeting compared to the lives of galaxies. A typical starburst phase lasts only 10 to 100 million years, a cosmic heartbeat in the lifespan of a galaxy. Yet in that short time, these events can transform their hosts dramatically. The massive, short-lived stars born during these periods die in supernova explosions within just a few million years, releasing enormous amounts of energy and enriching their surroundings with heavy elements like carbon, oxygen, and iron. These elements are the essential ingredients for planets, atmospheres, and life itself. In this way, starburst galaxies act as the chemical engines of the cosmos, manufacturing and distributing the building blocks of future generations of stars and worlds. However, the same energy that fuels their brilliance also sows the seeds of their demise. The collective winds and radiation from the massive stars eventually blow away the remaining gas, halting further star formation. When the burst ends, the galaxy is left gas-poor and often evolves into an elliptical or lenticular galaxy, a quiet reddish system populated mostly by older stars. In this sense, starbursts are both the climax and the conclusion of a galaxy's most active life stage, marking the transition from youthful exuberance to mature stillness. Astronomers studying starburst galaxies have also discovered a profound connection between these events and the growth of supermassive black holes. In many cases, the same inflows of gas that fuel starbursts also feed the central black hole, igniting it as an active galactic nucleus AGN. This connection suggests that starbursts and black hole activity are two sides of the same cosmic process. The transformation of gravitational energy into both starlight and the radiant fury of accretion. In galaxies like ARP 220, one of the nearest and most luminous ultra-infrared galaxies, intense star formation and AGN activity coexist, creating a system so bright in the infrared that it radiates more energy than an entire cluster of ordinary galaxies. Starburst galaxies also provide a glimpse into the early universe, when such frenetic activity was far more common. Observations from the James Webb Space Telescope and the Hubble Space Telescope have revealed countless young galaxies in the distant cosmos undergoing massive starburst events. These early star-forming galaxies, compact, irregular, and brilliant, are thought to be the ancestors of the mature galaxies we see today. Their violent energy output, supernova explosions, and winds helped shape the reionization epoch, when the first starlight transformed the universe from a dark, opaque sea of hydrogen into the transparent cosmos we now inhabit. The legacy of starburst galaxies is written across the universe. They are the alchemists of creation, enriching the cosmos with heavy elements, shaping galactic structures, and driving the evolution of both stars and black holes. Without these brief but furious episodes, the universe would be poor, dimmer, and perhaps even lifeless. Every atom of carbon in our bodies, every molecule of oxygen we breathe, was once part of the fire that burned within a starburst galaxy, scattered across time and space by the explosions of ancient suns. And so, as we gaze upon these blazing galaxies, we are looking not just at fireworks, but at cosmic forges, at the crucibles of existence. They remind us that the universe's greatest beauty often arises from its most turbulent moments, that creation and destruction are not opposites, but partners in an endless cycle. From these luminous outbursts of the nearby cosmos, our journey now carries us deeper into time, billions of years into the past, to witness the first galaxies themselves taking shape amid the darkness of the early universe. With the light of telescopes like Hubble and JWST guiding our view, we'll now explore galaxies through cosmic time, where the earliest structures reveal how the universe grew from chaos into the grand design we see today. When we gaze deep into the night sky, we are not merely looking across space, We are, again, looking back through time. Every distant galaxy we see is an image from the past, its light traveling across billions of years before reaching our eyes. The farther away we look, the younger the universe becomes. With modern telescopes like Hubble and JWST, humanity has learned to pierce that temporal veil, glimpsing the cosmos as it was mere hundreds of millions of years after the Big Bang. And what we see in those earliest epochs is a universe utterly unlike the grand structured cosmos we inhabit today. A universe of chaotic, irregular proto-galaxies, where the first sparks of starlight ignited in a sea of darkness, and where the great galaxies of today were still gathering, fragment by fragment, from the raw material of creation. Roughly 13.8 billion years ago, the universe began as a hot, dense fireball of energy and matter. For the first few 100,000 years, it was opaque. A blinding plasma of particles and photons endlessly scattering off one another. But as it expanded and cooled, protons and electrons combined to form neutral hydrogen, allowing light to travel freely for the first time. That ancient light, stretched by cosmic expansion, now fills the sky as the cosmic microwave background radiation, the afterglow of the Big Bang. Yet after this event, the universe entered a long, dark age. For nearly 400 million years, there were no stars, no galaxies, only cooling hydrogen gas and the gravitational seeds of structure planted by tiny quantum fluctuations from the earliest moments of existence. Then gravity began its quiet work. The invisible dark matter, the universe's dominant mass component, clumped together first, forming vast halos and filaments. These became gravitational wells that drew in ordinary matter, the hydrogen and helium gas that would eventually condense into stars. Within these halos, the first proto-galaxies began to form. Small chaotic systems only a few hundred light-years across, filled with massive, short-lived stars. These early galaxies, known as Population 3 galaxies, were unlike anything that exists today. Their stars were composed almost entirely of hydrogen and helium, with virtually no heavier elements because none had yet been forged. These stars burned hotter and brighter than any that came after, living for only a few million years before dying in colossal supernova explosions that enriched the surrounding space with heavier elements than carbon, oxygen, and iron, the essential building blocks of planets and life. The Hubble Space Telescope, launched in 1990, was humanity's first true time machine. By peering deeper into the cosmos than any telescope before it, Hubble revealed galaxies at distances corresponding to billions of years in the past. Its ultra-deep field and extreme deep field images, the result of hundreds of hours of exposure, unveiled thousands of faint galaxies packed into tiny regions of sky no larger than a grain of sand held at arm's length. These observations showed that the early universe was teeming with small, irregular galaxies, clumpy and chaotic, often merging into one another. There were few grand spirals or majestic ellipticals then. Instead, the cosmos was a restless sea of proto-galactic fragments, the raw ingredients that would later combine into the galaxies we see today. Each of those tiny misshapen galaxies in the early universe represents a work in progress, a snapshot of galactic evolution underway. Many of them appear blue, their light dominated by massive young stars. They are compact, dense, and turbulent, their gas reservoirs collapsing rapidly under gravity. As they merge, their collisions ignite bursts of star formation, setting off the same processes we now observe in modern starburst galaxies, but on a far grander and more chaotic scale. Over hundreds of millions of years, these small systems coalesce into larger ones, their gravitational interactions smoothing out their shapes and forming disks or spheroids. By about 3 to 4 billion years after the Big Bang, many of the familiar galactic morphologies, spirals, ellipticals, lenticulars, began to emerge. But for all its discoveries, Hubble could only see so far. The most distant galaxies it could detect dated to about 500 million years after the Big Bang, limited by its optical and near-infrared sensitivity. To go further, to see the very first galaxies forming out of darkness. Humanity needed a telescope that could observe in longer wavelengths, capable of capturing the faint infrared light stretched by billions of years of cosmic expansion. That telescope is the James Webb Space Telescope, JWST, launched in December 2021. And it has transformed our view of cosmic history beyond what even the most optimistic astronomers had imagined. JWST's infrared vision allows it to peer through clouds of dust and into epochs inaccessible to Hubble. In its first months of operation, JWST shattered previous distance records, revealing galaxies from when the universe was only 200 to 300 million years old, a mere 2% of its current age. These early galaxies are astonishingly bright and surprisingly mature, some already containing massive amounts of stars and dust. This discovery challenges previous models, suggesting that galaxy formation may have occurred much faster and more efficiently than once thought. Where astronomers expected to find faint, primitive smudges of light, JWST has instead uncovered well-formed systems, miniature versions of modern galaxies, complete with complex structures and potential hints of a spiral organization. One such example is the galaxy Glass 13, one of the earliest and most distant galaxies ever observed, whose light has traveled for over 13.4 billion years to reach us. Another CEERS 93316, detected in JWST's Cosmic Evolution Early Release Science Survey, may date to just 250 million years after the Big Bang, making it one of the universe's first substantial star cities. These galaxies shine brightly in JWST's infrared images, their colors revealing the signatures of newly formed stars and early chemical enrichment. Some appear redder not because of age, but because their light has been stretched by the universe's expansion, a phenomenon known as cosmological redshift. JWST's findings have deepened the mystery of how galaxies assembled so quickly. According to the traditional cosmological models, it should take hundreds of millions of years for dark matter halos to accumulate enough gas to form stars and grow into stable systems. Yet many of the galaxies JWST has observed already contain billions of solar masses and stars, suggesting that star formation in the early universe was incredibly efficient. It may be that the first stars and black holes formed together, their feedback processes accelerating the formation of galaxies. Alternatively, we may be glimpsing the gravitational effects of primordial dark matter structures, cosmic scaffolds that allowed galaxies to grow faster than we previously believed possible. Beyond the first galaxies, JWST has also begun to capture the transition from primordial chaos to order. The moment when small, irregular galaxies merge into larger, more structured systems. In its deep field observations, we see galaxies caught mid-collision, their gas and stars torn into filaments and arcs. These mergers, though violent, are essential to galactic evolution. They mix stellar populations, trigger starbursts, and ultimately give rise to the massive, stable galaxies that populate the modern universe. Over billions of years, this process of hierarchical merging transformed a universe of small blue star-forming systems into the grand spirals and ellipticals we recognize today. The light from these ancient galaxies carries profound meaning. It is not just a record of distant objects, it is a record of our own cosmic origins. The atoms in our bodies, the oxygen in our lungs, the iron in our blood, all were forged in the hearts of those early stars, the first generations that burned in these primordial galaxies. Every photon that reaches us from that epoch tells part of our story, the story of how the universe went from formless darkness to starlit wonder. And so, as JWST continues to peer deeper into time, we are beginning to piece together the most fundamental chapter of cosmic history. How structure arose from chaos, how galaxies grew from the faintest ripples of matter into the luminous beacons that fill the night sky. Yet even as we study their light, we find another mystery encoded within it. The colors of galaxies, the subtle hues that reveal their age, composition, and life cycle. To understand these colors is to understand how galaxies live, evolve, and die, and how the universe paints its grand masterpiece across billions of years. In the immense darkness of space, galaxies are the universe's brushstrokes of color, luminous swirls of light painted across the cosmic canvas. To the unaided eye, the night sky may appear only in shades of white and gray, but through the eyes of telescopes, the universe reveals its true palette. Brilliant blues, glowing yellows, deep reds, and even the faint, ghostly greens of ionized gases. These colors are not mere decoration. They are the fingerprints of time, chemistry, and evolution. Every hue in a galaxy's light tells a story about the stars within it, their ages, temperatures, and fates. And by reading this light, astronomers can reconstruct the life cycle of galaxies across billions of years. A galaxy's color is primarily determined by the types of stars it contains. Young, hot stars, massive, short-lived, and fiercely luminous, burn blue and white. They emit intense, ultraviolet light, their brilliance dominating regions where star formation is active. These stars live fast and die young, often within just a few million years, exploding as supernovae and leaving behind neutron stars or black holes. Their blue glow signifies youth and vigor, the cosmic equivalent of a galaxy's springtime. By contrast, older stars, smaller and cooler, emit more red and yellow light. These stars, often in their twilight years, burn hydrogen slowly and steadily. A galaxy glowing in soft orange or deep red is a mature system, where star formation has slowed or ceased entirely, and the remaining stars are ancient survivors from an earlier age. This relationship between color and stellar population allows astronomers to use color as a cosmic clock. By measuring a galaxy's spectrum, the distribution of its light across different wavelengths, they can infer not only the ages of its stars, but also their chemical composition, or metallicity. In astronomy, metals refer to all elements heavier than hydrogen and helium, produced through stellar fusion and supernova explosions. Young galaxies, formed soon after the Big Bang, contain mostly hydrogen and helium, and thus appear bluer and more pristine. Over time, as generations of stars live and die, they enrich the surrounding gas with heavier elements like oxygen, nitrogen, silicon, and iron. These metals alter the light of new stars, giving galaxies warmer tones and allowing astronomers to trace their chemical evolution through color. The blue galaxies we see today, such as the Pinwheel Galaxy, M101, or the Whirlpool Galaxy, M51, are active star factories. Their spiral arms are filled with vast clouds of gas and dust, where new stars are born in luminous clusters. These galaxies glow with a bluish tint because their light is dominated by massive O-type and B-type stars, the hottest and brightest in the stellar spectrum. In long exposure images, these galaxies appear vibrant and youthful, their light pulsating with energy. Astronomers often refer to them as blue cloud galaxies, part of a population that lies along a well-defined region in galactic color magnitude diagrams, a kind of census chart that maps brightness against color. The blue cloud represents the actively star-forming galaxies, those still alive with creation. In contrast, red galaxies, often ellipticals or lenticulars, are relics of a bygone era of star formation. Their light comes from long-lived, cooler K-type and M-type stars, which can burn for tens or even hundreds of billions of years. These galaxies have exhausted or lost their interstellar gas, leaving little material to form new stars. Without the blue light of young stars to balance their color, they appear as glowing embers in the cosmic night. These red sequence galaxies occupy another distinct region on the color magnitude diagram, marking the final stage of galactic evolution. Between these two populations lies a transitional zone known as the Green Valley, home to galaxies in the process of shutting down their star formation. Over time, galaxies migrate from the blue cloud to the red sequence, their colors shifting as they age and grow quiet. Astronomers use this color evolution to map the life cycles of galaxies across cosmic history. A galaxy may begin its life in brilliant blue, forming stars at a furious rate, then fade into gold and crimson as it matures and its star formation slows. Some galaxies can even be rejuvenated, a process known as galactic rejuvenation. When they interact or merge with gas-rich companions, reigniting star formation and briefly returning to the blue cloud before fading once again. In this way, the universe's color palette is dynamic, a living record of growth, decay, and renewal. Color also serves as a key diagnostic tool for measuring galactic distance and motion. Because the universe is expanding, the light from distant galaxies is stretched, a phenomenon known as redshift. The farther away a galaxy is, the faster it recedes, and the more its light is shifted toward longer, redder wavelengths. By measuring this redshift, astronomers can calculate not only how far away a galaxy lies, but also how fast the universe was expanding when that light first set out on its journey. The deep red hues of the earliest galaxies, as captured by the James Webb Space Telescope, are therefore both a sign of age and of distance. The light of youth seen through the lens of time. The interplay of color also reveals the hidden forces shaping galaxies. For instance, galaxies undergoing starburst events, periods of intense star formation triggered by mergers or gas inflows, often display a mix of vivid blues and warm reds, as regions of new stars coexist with older stellar populations. On the other hand, galaxies hosting active galactic nuclei AGN can show unusual colors caused by radiation from their central black holes, which can heat dust and to emit infrared light. By analyzing these color signatures, astronomers can distinguish between galaxies dominated by star formation and those powered by black hole activity, tracing how energy flows between the two processes over cosmic time. Observations from Hubble and JWST have allowed scientists to track how the universe's overall color has changed throughout its history. In the earliest epochs, within the first few billion years after the Big Bang, galaxies were predominantly blue, their light dominated by young, hot stars. As the universe aged, star formation gradually declined, and more galaxies transitioned into the red sequence. Today, the universe's average color is closer to a faint beige, sometimes poetically described as cosmic latte. This soft hue represents the balance between aging red galaxies and the still active blue ones, a cosmic equilibrium between creation and decay. Beyond the science, the color of galaxies connects us to something deeply poetic, the understanding that we too are part of this chromatic evolution. The elements that make up our bodies were born in the hot blue hearts of massive stars and spread across the universe through supernova, becoming part of the next generation of galaxies. The red light of old stars and the blue glow of young ones are, in essence, the heartbeat of the cosmos. A pulse that has been beating for nearly 14 billion years. Every color we observe in the universe is a note in that symphony, every hue a memory of creation itself. In this interplay of color and time, astronomers have found not just a way to measure the universe, but a way to read its autobiography. The record of how matter became light and how light became the story of everything. The color of galaxies in all its subtlety and range is the language of cosmic evolution, written in the spectrum of eternity. And as we move forward in our journey through this universal narrative, we now turn from color to form, to the shapes that galaxies take as they evolve. For the universe is not just painted in light, it is sculpted in structure. Our next step takes us into the realm of the shapes of the cosmos, where galaxies are classified by their design, spirals, ellipticals, and irregulars, and where the great Hubble tuning fork diagram reveals the taxonomy of the universe's vast and varied creations. When we gaze upon the night sky, the light of galaxies may seem chaotic, vast scattered islands of stars adrift in a cosmic sea, but beneath that apparent randomness lies an underlying order, a taxonomy of structure that mirrors the very rhythm of cosmic evolution. This order was first articulated by one of the 20th century's great astronomers, Edwin Hubble, who in the early 1900s devised a system to classify galaxies based on their shapes and structures. What emerged from his observations was a simple yet profound diagram, the Hubble tuning fork, a visual key that remains one of the most powerful tools in understanding how galaxies form, evolve, and transform across billions of years. At its core, the Hubble tuning fork diagram is a map of galactic morphology, a way to categorize the various shapes that galaxies take as they mature. The diagram begins with a single handle on the left representing elliptical galaxies and splits into two prongs on the right representing spiral galaxies, both barred and unbarred. Beyond these lie the irregular galaxies, those that defy easy classification, appearing as the cosmic outliers. Though it may look simple, this branching structure captures the essential diversity of galactic forms, offering a visual summary of the universe's dynamic processes. Hubble's classification began with the ellipticals, E0 to E7, smooth, featureless galaxies that range from nearly spherical, E0, to elongated, cigar-shaped forms, E7. These systems are typically composed of older, redder stars and contain little gas or dust. Their appearance is tranquil and uniform, lacking the bright spiral arms or dust lanes seen in younger galaxies. Hubble placed them at the stem of his tuning fork because he originally believed they might represent the earliest stage of galactic evolution, primordial systems that later flattened and spun up into spirals. While modern astronomy has since revised this interpretation, Hubble's intuition about the relationship between form and evolution was not far from the truth. Ellipticals, as we now know, often form through the mergers of spiral galaxies, their collisions scrambling stars into random orbits and depleting the gas needed for a new star formation. In a sense, the ellipticals are the elder galaxies, shaped by time and gravitational encounter. From the stem, Hubble's diagram forks into two branches representing spiral galaxies. The upper branch contains ordinary spirals, S, while the lower branch holds barred spirals, SB, those that feature a bright linear bar of stars cutting through the central bulge. Each branch progresses from early to late types, labeled A, B, and C, or sometimes extending to D, depending on how tightly wound the spiral arms are and how large the central bulge appears. For example, an S a galaxy has tightly wrapped arms and a prominent bulge, whereas an SC galaxy has loose, open arms and a smaller, more diffuse core. The barred versions, SBA, SBB, SBC, follow the same pattern, differing mainly in the presence of the bar, which channels gas toward the galaxy's center and often fuels star formation or black hole activity. Our own Milky Way is believed to be an SBBC galaxy, a barred spiral with moderately open arms and an active central bar structure. In the Hubble diagram, it would sit midway down the lower fork, a galaxy in balance between order and energy, between maturity and ongoing creation. Nearby, the Andromeda galaxy, M31, falls on the upper branch as an SB type, its arms more tightly wound and its bulge more pronounced. The Whirlpool galaxy, 1M51, with its grand symmetric spirals, stands as a textbook example of an SC type. A galaxy still vigorously forming stars along its luminous arms. Each of these categories represents not just a shape, but a state of being, a reflection of how a galaxy's history, environment, and composition have sculpted it over time. Yet not all galaxies conform neatly to the tuning fork. Beyond its branches lie the irregular galaxies, those whose forms are distorted, chaotic, or disrupted, often by gravitational interactions or collisions. Hubble placed these at the far end of his diagram, acknowledging that some galaxies simply do not fit the mold. The large and small Magellanic Clouds, which orbit the Milky Way, are prime examples. Asymmetrical, gas-rich systems teeming with star-forming regions but shaking the coherent structure of spirals or ellipticals. These irregulars remind us that while the classification brings order, the universe itself remains inherently dynamic and unpredictable. Hubble's diagram was revolutionary not just for its elegance, but for its insight into galactic evolution. Though he initially believed galaxies might evolve along the tuning fork's path, from ellipticals to spirals, later discoveries revealed a more complex story. Instead of a linear progression, galaxies morph between categories through cosmic processes. Collisions between spirals can create ellipticals. The accretion of gas can transform an elliptical into a disk galaxy. Tidal forces can warp and twist galaxies into irregular shapes. The tuning fork, then, is not a timeline but a snapshot of possible states, a map of how galaxies exist and evolve within a continuum of gravitational and chemical change. In the decades since Hubble's time, astronomers have refined and expanded his classification system. The Irregular system, for instance, introduced finer distinctions, including intermediate stages between ellipticals and spirals, such as lenticular galaxies, S0, which bridge the gap between the two. Lenticulars have the flattened disks of spirals but lack prominent arms, often representing galaxies that have exhausted or lost their gas and ceased star formation. They are, in essence, spirals frozen in transition, suspended between youth and old age. Other refinements have added categories for peculiar galaxies, ring galaxies, and ultra-diffuse galaxies, each revealing new layers of complexity in the cosmic story. Despite these refinements, the Hubble tuning fork endures as one of astronomy's most enduring and intuitive tools. It captures, in a single image, the diversity of galactic life and the interplay between structure, motion, and age. More than a century after its conception, it remains a cornerstone of galactic studies, a symbol of how human curiosity transforms the vastness of the cosmos into something we can understand and categorize. Modern telescopes have confirmed that the Hubble sequence reflects real physical differences. Spiral galaxies are typically rich in cold gas and dark matter, allowing them to sustain star formation over billions of years. Ellipticals, on the other hand, are dominated by hot gas and old stars, the result of past mergers that have consumed or ejected their star-forming material. These structural and compositional contrasts reveal how environment and interaction shape galactic destiny. Galaxies in dense clusters, for example, are more likely to be ellipticals, stripped of gas by gravitational tides or ram pressure effects, while isolated galaxies in the cosmic field tend to remain spirals, evolving more peacefully. Thus, Hubble's simple fork diagram becomes a cosmic genealogy, showing not just what galaxies look like, but how they live, age, and die. It embodies the universal truth that form follows history, that every curve, bulge, and spiral arm is the product of billions of years of motion, collision, and transformation. Each galaxy is a page in the cosmic archive, and the tuning fork is our index to that vast, interconnected story. And yet not everything that defines a galaxy can be seen in visible light. Beyond the optical spectrum lies an entire hidden universe. Galaxies glowing in radio waves, infrared heat, ultraviolet radiation, and even high-energy X-rays and gamma rays. These invisible wavelengths reveal secrets that optical telescopes cannot. Cold gas clouds where stars are about to form, hot plasma near black holes, and powerful jets that span millions of light years. To truly understand galaxies in all their dimensions, astronomers must go beyond what the eye can see. To observe the unseen and unveil the full electromagnetic symphony of the cosmos. In the great theater of the universe, the light we see with our eyes, the visible spectrum, is but a single octave in an infinite symphony. The galaxies that adorn our telescopic images, glowing with starlight and dust, are only part of the story. Beyond what the human eye can perceive lies an invisible cosmos, radiating across radio waves, infrared heat, ultraviolet rays, X-rays, and gamma rays. Each band of the electromagnetic spectrum revealing a different aspect of galactic life. To understand galaxies fully, to see not just their stars, but their souls. Astronomers have learned to look beyond light itself. They have built instruments that can translate the unseen into vision, transforming silent frequencies into knowledge. Through these lenses, we glimpse black holes feeding in darkness, stars being born in cold gas clouds, and magnetic fields stretching like invisible threads through interstellar space. It was only in the 20th century that humanity began to open these new windows to the universe. Before then, astronomy was a science of visible light, limited to what optical telescopes could reveal. But in 1931, an engineer named Karl Jansky detected mysterious radio signals coming from the Milky Way, the birth of radio astronomy. Soon after, astronomers like Grote Reber began mapping the sky in radio waves, uncovering vast, previously invisible structures. Through radio telescopes, the universe appeared utterly transformed. Where optical images showed darkness, radio maps revealed sprawling clouds of cold hydrogen, immense jets of plasma, and galaxies glowing with the after effects of cosmic violence. Radio astronomy unveiled a universe of motion and magnetism. Galaxies like MM 87, for instance, appear serene in visible light, a smooth elliptical shape. But in radio wavelengths, M87 reveals a colossal jet of charged particles shooting from its core at nearly the speed of light, powered by its supermassive black hole. The VLA, Very Large Array, in New Mexico, with its 27 giant antennas, and ALMA, Atacama Large Millimeter/Submillimeter Array, in Chile, perched high in the desert air, have made such discoveries routine. These instruments allow scientists to map the cold molecular gas, primarily hydrogen and carbon monoxide, from which stars are born. They reveal spiral galaxies laced with complex networks of magnetic fields, guiding the flow of cosmic dust and charged particles. Through radio observations, astronomers have learned that even the emptiest regions of space hum with energy, shaped by invisible magnetic forces that thread through galaxies like cosmic veins. If radio waves uncover the coldest regions of the cosmos, infrared light reveals the warm, hidden glow of dust-shrouded stars and nebulae. Much of the universe's starlight is absorbed by interstellar dust and re-emitted in infrared wavelengths, making this part of the spectrum essential for understanding galactic evolution. The Spitzer Space Telescope, launched in 2003, and its successor, the James Webb Space Telescope, JWST, have revolutionized infrared astronomy, allowing us to peer through the dusty veils that conceal stellar nurseries and galactic cores. In infrared images, galaxies once obscured by darkness come alive, revealing dense star-forming regions, colliding galaxies, and hidden black holes wrapped in cocoons of gas. Infrared observations are particularly powerful for studying distant galaxies. As the universe expands, the light from ancient galaxies is stretched or redshifted into longer wavelengths, often far beyond the visible range. By observing in the infrared, telescopes like JWST can capture this ancient light, allowing astronomers to see galaxies as they were over 13 billion years ago, during the universe's earliest epochs. In the glow of these distant systems, we find the first signs of star formation and galactic structure, offering clues to how the cosmic web itself took shape. Infrared astronomy also reveals the cool interstellar medium, the dust and molecular clouds that form the raw material for new stars. These clouds emit faint infrared light as they are warmed by nearby stars, marking the places where stellar creation is underway. At higher energy still, X-ray astronomy peels back another layer of the cosmic mystery. X-rays are produced by some of the universe's most violent and energetic phenomena. The accretion disks around black holes, the hot gas in galaxy clusters, and the remnants of supernova explosions. Because X-rays cannot penetrate Earth's atmosphere, astronomers must send their detectors into space aboard satellites such as Chandra, XMM Newton, and NuSTAR. Through their eyes, we see galaxies not as placid collections of stars, but as boiling cauldrons of energy. One of the most striking X-ray images ever taken is that of the Perseus cluster, a massive assembly of galaxies located about 240 million light-years away. In visible light, it appears as a cloud of faint, fuzzy galaxies, but in X-rays, it glows like a cosmic inferno, filled with gas, heated to tens of millions of degrees by collisions and black hole activity. At its center, a supermassive black hole emits powerful jets that carve bubbles and ripples into the surrounding plasma, generating waves that echo through space like sound. Similarly, in our own galaxy, X-ray telescopes have captured the chaotic brilliance of the region around Sagittarius A, revealing flares of high-energy radiation as matter spirals toward the event horizon. X-ray observations also expose the hidden skeletons of galaxies, the remnants of stellar death. The explosions of supernovae scatter elements across galaxies and leave behind neutron stars and black holes, which emit powerful X-rays as they accrete matter from surrounding gas. By mapping these emissions, astronomers can trace the cycle of stellar life and death, understanding how galaxies recycle their material across cosmic time. In fact, without X-ray astronomy, we would know little about the processes that regulate galaxy evolution, how black holes heat their environments, how star formation is quenched, and how clusters of galaxies maintain their delicate balance between collapse and expansion. But even X-rays are not the end of the story. At the highest energies of all lies the realm of gamma-ray astronomy, where the universe reveals its most extreme events. Supernovae, pulsars, active galactic nuclei, and gamma-ray bursts. These bursts, sometimes lasting only seconds, can release more energy than the Sun will emit over its entire lifetime. Instruments like the Fermi Gamma Ray Space Telescope and ENTEDG-RAL detect these fleeting flashes, tracing them to the deaths of massive stars, the mergers of neutron stars, or the furious jets of distant quasars. In gamma rays, the universe is a place of unimaginable violence and power. A cosmic fireworks display where black holes and magnetic fields twist matter and energy into forms beyond human comprehension. By combining data from across the electromagnetic spectrum, astronomers can build multi-wavelength portraits of galaxies, holistic images that reveal their full complexity. A spiral galaxy seen in visible light shows graceful arms of stars. In radio, it reveals vast hydrogen clouds. In infrared, it glows with the heat of newborn suns. In X-rays, its core blazes with the fury of black hole accretion. And in gamma rays, it crackles with high-energy particles accelerated by supernovae and cosmic rays. Each wavelength adds a new layer of understanding, like the instruments of an orchestra coming together to perform a single cosmic symphony. This multispectral approach has fundamentally changed our understanding of the universe. It has shown us that galaxies are not static collections of stars, but dynamic ecosystems. Systems of gas, dust, dark matter, radiation, and magnetic fields, all interacting in a delicate balance. It is revealed that even in the depths of space, nothing is truly dark. Every region of the universe glows with energy, if only we have the right eyes to see it. And yet, for all our technological reach, the story of galaxies is still not complete. Beyond their light, visible or invisible, lies their role as cradles of planets, as forges of solar systems, and perhaps as the nurseries of life itself. For in the quiet corners of these galaxies around unremarkable stars, small rocky worlds orbit, and on at least one of them, beings have risen to look back into the cosmos and ask how it all began. From the electromagnetic symphony of galaxies, our journey now turns inward to the planetary realms that form within them, to the question of how galaxies become cradles of planets and potential life in the vast cosmic expanse. When we think of galaxies, we often imagine them as grand, majestic swirls of stars, cosmic masterpieces glowing in the infinite dark. Yet beyond their splendor, galaxies are something far more profound. They are the cradles of planets, the wombs of life itself. Within their glowing arms and quiet halos lie not just stars, but billions upon billions of worlds, each one orbiting its sun in silent cosmic harmony, each one a potential stage for the story of existence to unfold. The universe, viewed through this lens, becomes not merely a spectacle of physics and light, but a vast living continuum. A place where chemistry becomes biology, where dust becomes consciousness, and where galaxies serve as the nurseries of life's possibility. Every galaxy, from the smallest dwarf to the mightiest elliptical, is a factory of matter and meaning. The stars that illuminate their disks are not isolated points of light. They are forges, alchemists transmuting hydrogen into helium and heavier elements, carbon, oxygen, silicon, and iron, the essential ingredients of planets and life. These elements are released into the galaxy through stellar winds and the cataclysmic explosions of supernovae, enriching the interstellar medium with the raw material for new generations of stars and planetary systems. In this way, galaxies are self-sustaining ecosystems, each generation of stars laying the groundwork for the next, each wave of creation seeding the potential for life to one day emerge. Consider our own Milky Way, which contains roughly 100 to 400 billion stars, and likely an equal or greater number of planets. The Kepler Space Telescope, launched in 2009, revolutionized our understanding of planetary abundance. Before Kepler, the existence of planets around other stars, exoplanets, was only suspected. Now we know that planets are ubiquitous. Nearly every star in the Milky Way is thought to host at least one planet, and many have entire systems. This means that in our galaxy alone, there could be hundreds of billions of worlds, and across the observable universe, with its 2 trillion galaxies, there may exist a sextillion planets. That's a 1 followed by 21 zeros. It is a number so vast that it defies imagination, a cosmic ocean of worlds scattered across space and time. But not all planets are created equal. The vast majority are likely barren, frozen wastelands or scorched infernos orbiting too far or too close to their suns. Yet within this immense diversity lies a smaller subset. Planets located in the habitable zone of their stars, where conditions allow for liquid water, the most essential ingredient for life as we know it. Astronomers refer to this as the Goldilocks zone, where it's neither too hot nor too cold, but just right. Kepler and subsequent missions like TESS, Transiting Exoplanet Survey Satellite, have identified thousands of such potentially habitable worlds, and statistical analysis suggests that in our galaxy alone, there could be tens of billions of Earth-sized planets orbiting within these life-friendly zones. The formation of these planets is a natural byproduct of stellar evolution. When a star forms from a collapsing cloud of gas and dust, the residual material flattens into a rotating disk. Within this protoplanetary disk, dust grains collide and stick together, forming clumps that grow into planetesimals and eventually into full-fledged planets. Observations from telescopes like ALMA, Atacama Large Millimeter, /Submillimeter Array, and JWST have captured breathtaking images of these disks around young stars. Swirling rings of gas and dust with dark gaps where planets are already forming. Each one of these systems represents a microcosm, a miniature galaxy in its own right, bound by gravity and illuminated by its central star. The chemical diversity of galaxies plays a crucial role in determining the habitability of the planets they produce. Galaxies rich in heavy elements, what astronomers call metal-rich galaxies, are more likely to form rocky, Earth-like planets, since these elements are needed to build solid surfaces and atmospheres. Spiral galaxies like the Milky Way, which are still actively forming stars and recycling material, are particularly fertile grounds for planet formation. In contrast, ancient elliptical galaxies, dominated by older stars and depleted of gas, are less likely to host new planets, though they may still contain ancient systems formed in their youth. Thus, galaxies themselves possess a kind of chemical age, with their metallicity acting as a barometer of their potential for hosting habitable worlds. Yet the presence of planets does not guarantee the presence of life. For life to arise, a delicate balance of factors must coincide. Stable orbits, protective to magnetic fields, geological activity to recycle nutrients, and perhaps even the right kind of cosmic neighborhood. The Milky Way's habitable zone, for example, is thought to lie roughly between 7,000 and 9,000 parsecs from its center, far enough to avoid destructive radiation from the galactic core, yet close enough to access the metals produced by countless generations of stars. Our Sun resides comfortably within this zone, orbiting in a relatively quiet region of the Orion Arm, a cosmic suburb far from the galaxy's turbulent heart. But if our galaxy alone contains billions of potentially habitable planets, and there are 2 trillion galaxies in the observable universe, then the odds of life existing elsewhere become staggering. Even if life arises on only a tiny fraction of those worlds, say 1 in a million, the number of living planets could still exceed billions upon billions. Somewhere in the spiral arms of distant galaxies there may be oceans beneath alien skies, forests under strange suns, and perhaps civilizations gazing upward, wondering, as we do, if they are alone. And yet, despite the statistical certainty of life's possibility, we have yet to find direct evidence of it. The Fermi paradox. The question of why, in such a vast and ancient universe, we have not yet detected signs of extraterrestrial intelligence remains one of the great mysteries of science. Perhaps life is rare, a cosmic miracle requiring conditions so precise they occur only occasionally. Or perhaps life is common, but intelligence is fragile. A brief flicker easily extinguished by the forces of nature or due its own creation. It may even be that the distances between galaxies are simply too immense, the speed of light too slow for civilizations to bridge the cosmic gulf. Still, the cosmic principle of mediocrity, the idea that our place in the universe is not special, suggests otherwise. If the laws of physics and chemistry are the same everywhere, then life, too, should emerge wherever conditions allow. Galaxies, then, are not just collections of stars, but cosmic incubators, scattered across the universe like seeds in an infinite field. Each one holds within it the potential for consciousness, for beings who might one day look up at their own skies and see the faint glow of other galaxies, wondering if those distant lights too harbor life. The implications of this are as humbling as they are exhilarating. When we look at a galaxy 100 million light years away, we are not just seeing light, we are looking at possibility. In the soft glow of those distant stars, there may be countless worlds with oceans, clouds, and continents. There may be creatures evolving, civilizations dreaming, and minds pondering the same cosmic questions we now ask. In that sense, the galaxies are not distant at all. They are reflections of our own potential, our shared cosmic heritage written in starlight. And yet, even among this endless abundance, there exists a boundary. The edge of the observable universe, beyond which light has not yet reached us. Beyond that edge lies the unknown. Galaxies whose light is still traveling toward us, whose stars were born when time itself was young. To venture there, even in imagination, is to approach the cosmic horizon, the ultimate limit of sight and understanding. Our next journey takes us to that horizon, to the very edge of the observable universe, where the first galaxies shimmer faintly in the ancient light of creation, and where time and space themselves merge into mystery. At the outermost boundary of human perception lies a frontier so distant, so ancient, that it is as much a limit of time as it is of space, the edge of the observable universe. Beyond this horizon, the cosmos continues, perhaps infinitely, but its light has not yet had time to reach us. Everything we can see, from the nearest stars to the faintest galaxies captured by our most powerful telescopes, exists within a sphere roughly 93 billion light-years across. This is not the edge of the universe itself. The universe likely extends far beyond, but rather the edge of the visible past, the point beyond which light, the fastest messenger in existence, has been stretched and slowed by the expansion of space until it can no longer reach our eyes. The galaxies we observe near this cosmic boundary are not just far away, they are ancient. Their light has been traveling toward us for over 13 billion years, emitted when the universe was only a few 100 million years old. By the time that light arrives, it carries with it the faint echo of the early cosmos, a message written in wavelengths stretched by time and distance. This stretching is known as cosmological redshift, one of the most profound consequences of an expanding universe. To understand this redshift, imagine the universe as an ever-expanding fabric of space-time. As galaxies drift apart, the very space between them stretches, and the light traveling through that space is stretched with it. Its wavelength lengthens, moving from the energetic blues and whites of visible light into the deep reds and eventually into the infrared and microwave portions of the spectrum. Thus, a galaxy that once shone an ultraviolet brilliance billions of years ago now appears as a faint red smudge in our telescopes. The greater the redshift, the farther away, and the older the galaxy is. This redshift is not caused by the galaxies themselves moving through space, but by the expansion of space itself. When we say that a galaxy is 13 billion light-years away, we do not mean that it sits at that distance now. Rather, that is how long its light has taken to reach us. In reality, as the universe has continued to expand during that time, those galaxies are now more than 30 billion light-years away. The cosmic horizon, then, is not a fixed wall, but a moving boundary, a limit that retreats faster than light can travel, ensuring that some regions of the universe will remain forever beyond our view. The most distant galaxies known, observed by the James Webb Space Telescope, JWST, lie at redshifts greater than 13, meaning we see them as they were when the universe was only about 300 million years old. These faint infant galaxies appear as delicate sparks of light, each containing only a few million stars, cosmic embryos forming from the primordial hydrogen and helium left over from the Big Bang. Their light, stretched into the infrared, reaches us as a whisper from the dawn of time, a testament to the universe's first moments of structure and illumination. JWST's deep field images have revealed dozens of these early galaxies, far surpassing the reach of Hubble. One of the most extraordinary examples, Galaxy 13, shines from just 320 million years after the Big Bang, the oldest starlight ever captured. When its light began its journey, the universe was in its infancy, filled with dense, glowing hydrogen clouds and the first stars igniting across the darkness. JWST's infrared eyes can detect this faint light because they are tuned precisely to the wavelengths into which the earliest galaxies' emissions have been redshifted. Where Hubble saw darkness, JWST sees a cosmos alive with youth, a tapestry of starbursts, collisions, and luminous beginnings. As we observe deeper, we begin to approach the epoch of ionization, the period when the first stars and galaxies flooded the universe with light, ending the cosmic dark ages. Before this time, the universe was opaque, filled with neutral hydrogen that absorbed and scattered radiation. When the first stars ignited, their ultraviolet light reionized the surrounding gas, allowing light to travel freely once more. This great transition, occurring between 400 million and 1 billion years after the Big Bang, marks one of the most profound transformations in cosmic history. The moment when the universe became transparent, and galaxies began to shine through the veil of primordial fog. The faint light from these early epochs carries more than just visual beauty. It encodes the physics of creation itself. By analyzing the redshift and brightness of distant galaxies, astronomers can reconstruct how matter clustered, how dark matter formed scaffolds for galaxy growth, and how dark energy began its subtle but relentless acceleration of cosmic expansion. Each photon arriving from that time is a data point in a story that spans nearly 14 billion years. A story of birth, evolution, and vast transformation. Beyond these first galaxies, we reach the cosmic microwave background, CMB, the farthest light that can ever be seen, the literal edge of the observable universe. This ancient radiation, released about 380,000 years after the Big Bang, is the afterglow of creation, the moment when the universe cooled enough for atoms to form, allowing light to travel freely for the first time. The CMB fills the universe uniformly, a faint glow of microwave radiation coming from every direction, its temperature only 2.7 Kelvin above absolute zero. To the naked eye, it is invisible. But radio and microwave telescopes like Planck and WMAP have mapped it with incredible precision, revealing tiny fluctuations in temperature, ripples that correspond to the seeds of galaxies, clusters, and cosmic structure. Those minuscule variations, 1 part in 100,000, are the fingerprints of everything that would follow. Standing at the edge of the observable universe, we are looking not just outward, but backward. Through layers of time, stacked like translucent pages of a cosmic book, the nearest galaxies show the universe as it is today. The most distant ones show it as it was billions of years ago, and the CMB shows it as it was before galaxies even existed. We are, in essence, surrounded by time, a spherical record of the universe's entire history, centered upon our tiny point in space. Yet beyond this horizon there is more, much more. The universe does not end where our vision fades. It continues indefinitely, perhaps infinitely. The light from those unreachable realms will never reach us because space itself expands faster than light can travel. These regions exist outside our cosmic horizon, real but forever hidden. They are the unobservable universe, the vast and unknowable realms that lie beyond the limits of light. To contemplate this boundary is to confront both the grandeur and the limitation of human existence. We stand on a small planet orbiting a modest star within one of hundreds of billions of galaxies. And yet, through the quiet patience of observation, we have seen nearly to the beginning of time itself. The edge of the observable universe is not a wall, it is a mirror of our curiosity, the frontier of what the cosmos allows us to know. But even as we peer into that ancient light, we must look forward as well. The universe continues to evolve, and galaxies continue to drift apart, carried by the accelerating expansion driven by dark energy. The future of these galaxies, and indeed of the cosmos itself, is one of transformation and fading light. A destiny written in the slow unfolding of time. As we journey onward, we will step beyond the edge of observation and into speculation, to explore what lies ahead for galaxies, stars, and the universe itself in the future of galaxies. The universe, vast and radiant as it is not eternal in its current form. Every shining galaxy, every star, every flicker of cosmic light exists within a grand story that is still being written. A story whose final chapters will be written not in brilliance, but in silence. As we look toward the future of galaxies, we are in truth looking toward the slow twilight of creation itself. What awaits the universe is a saga of transformation, of mergers, fading starlight, and the long descent into cosmic darkness. Even now, galaxies are moving. They are not fixed upon some celestial stage, but are carried along the expanding fabric of the universe. Their fates dictated by the gravity that binds them and the dark energy that drives them apart. In the local group, our own small cluster of galaxies, gravity still reigns over expansion. The Milky Way, Andromeda, M31, and the Triangulum Galaxy, M33, are engaged in a slow-motion dance that has lasted billions of years and will culminate in a breathtaking collision roughly 4.5 billion years from now. Astronomers have mapped this future with exquisite precision. The Andromeda Galaxy, currently 2.5 million light-years away, is approaching us at about 110 kilometers per second. When the two galaxies finally meet, they will not collide in the way solid objects do. Their stars are far too widely spaced for that. Instead, their immense gravitational fields will intertwine, pulling at each other's spiral arms, flinging vast streams of stars into intergalactic space, and compressing massive clouds of gas that will ignite bursts of star formation. For a time, the night sky will become a spectacle beyond imagination. Andromeda will grow until it fills the heavens, its bright core merging with the Milky Ways, its arms glowing with newborn stars. The Sun, by then nearing the end of its own life, will witness this transformation from a changed vantage, likely displaced into a new orbit, far from where it began. After billions of years of this slow, intricate merging, the two galaxies will settle into a single, massive, elliptical galaxy, sometimes referred to by astronomers as Milkomeda or Milkdromeda. The once distinct spiral structures will fade, their graceful arms stretched and smeared into a smooth spheroidal form. The new galaxy will shine with the combined light of 1 trillion stars, yet it will be quieter, calmer. A mature and stable remnant of cosmic evolution. While this galactic merger will mark a dramatic transformation for our local group, it is not unique. Throughout the universe, galactic mergers are the natural consequence of cosmic structure formation. Over the next tens of billions of years, small galaxies within clusters will continue to merge into larger systems, while galaxy clusters themselves will coalesce into even more massive conglomerates, superclusters collapsing into single giant elliptical galaxies bound tightly by gravity. But while local regions of the universe will grow more massive, the universe at large will grow more empty. This is because the cosmic expansion, driven by dark energy, is accelerating. Galaxies beyond our local group are already receding from us faster than ever, and beyond a certain distance they are moving away faster than the speed of light, not through motion but through the expansion of space itself. This means that in the far future, galaxies outside our gravitationally bound neighborhood will drift beyond our cosmic horizon, their light redshifted into invisibility. In roughly 100 billion years, observers in the merged Milkomeda galaxy will see only a handful of nearby galaxies in the night sky. The rest of the universe will have faded into a vast, silent darkness. For them, it will appear as if the cosmos has always consisted of just one galaxy, the ultimate illusion of isolation. Inside the galaxies that remain, the slow process of stellar aging will continue. Stars like our Sun will exhaust their hydrogen fuel and die, leaving behind white dwarfs, tiny dim embers of stellar light. Massive stars will end in spectacular supernova explosions, collapsing into neutron stars or black holes. Over trillions of years, even these remnants will cool and fade. The brightest beacons of the universe will vanish one by one, and the night skies of the distant future will dim into obscurity. New star formation will cease entirely when galaxies run out of gas. Already many massive ellipticals have entered this quiescent phase, their stellar nurseries long closed. Eventually, even galaxies like the Milky Way, once bustling with starbirth, will grow still. Without fresh gas to ignite new stars, the remaining ones will slowly age and die, turning the galaxy from a vibrant spiral into a collection of fading embers. Over time, galaxies will transform into vast fields of stellar remnants. White dwarfs, neutron stars, and black holes, orbiting in the dim light of their accumulated past. As time stretches beyond human comprehension, the cosmos will enter what physicists call the degenerate era, beginning around 10 to the 14th power, 100 trillion years from now. By then, nearly all stars will have burned out. The universe will be illuminated only by the faint glow of brown dwarfs, as failed stars that never ignited, and the soft infrared heat of cooling white dwarfs. Occasionally, two of these remnants may collide, sparking a brief flare of fusion, but such events will become exceedingly rare. Meanwhile, galactic mergers will continue, though at an ever slower pace. Over unimaginable timescales, the remaining galaxies within clusters will merge into single massive elliptical galaxies surrounded by halos of dark matter and black holes. These supergalaxies will drift in solitude through an ever-expanding void. Inside them, gravity will still reign locally. Black holes will continue to consume the remnants of stars and gas. But the larger universe will become increasingly still. Eventually, even black holes will begin to fade. According to Stephen Hawking's theory of Hawking radiation, black holes slowly lose mass by emitting faint radiation, evaporating over stupendous timescales. A typical stellar mass black hole will take about 10 to the 67th power years to evaporate completely, while the supermassive black holes at galactic centers will endure for perhaps 10 to the power of 100 years. A number so vast it dwarfs the age of the universe by an unimaginable factor. When the last of these titans finally vanishes in a whisper of quantum radiation, the universe will be left in a state of near total darkness. This ultimate epoch, known as the heat death or big freeze, will mark the final phase of cosmic evolution. By then, the universe will be a cold, diffuse sea of subatomic particles, photons, neutrinos, and electrons, drifting endlessly through an expanding void. The temperature of space will approach absolute zero, and entropy will reach its maximum. All processes that increase complexity, star formation, fusion, life, thought, will have long ceased. The universe will persist, but without change, without structure, without light. It will be eternal in duration, but empty in meaning, a vast cold equilibrium. Yet even this bleak vision holds a strange, haunting beauty. For every star that ever shone, every galaxy that ever formed, every atom of matter that ever coalesced into something greater, all of it existed because the universe allowed for it, if only for a while. The story of galaxies, from the first flickers of starlight to the last fading ember, is the story of transformation itself. Of creation emerging from chaos, of brilliance emerging from darkness, and of eventual silence reclaiming all. But before that silence arrives, there is still time. Billions upon billions of years in which stars will shine, planets will orbit, and life perhaps will continue to dream. And as we contemplate this grand arc of cosmic evolution, from birth to death, from fire to frost, we find ourselves drawn to one final reflection, one that brings the journey home. For in understanding the universe's destiny, we also come to understand our own place within it. A fleeting spark in the vastness of time, yet one capable of wonder, awareness, and meaning. Our next and final step, then, will take us into that realm of reflection, the cosmic perspective, where science meets awe, and where the The immensity of the universe reminds us not of our insignificance, but of our connection to all that ever was and will be. As we arrive at the end of our journey, a journey that has carried us from the glowing arms of the Milky Way to the silent edge of the observable universe, we are left with a sense of both humility and transcendence. The cosmos in all its vastness dwarfs us beyond measure, and yet it also includes us. The atoms that make up our bodies were forged in the hearts of long-dead stars. The calcium in our bones, the iron in our blood, the oxygen in our lungs, all were born in ancient galaxies that lived, died, and gave their elements back to the universe so that billions of years later, we might open our eyes and wonder. We are small, impossibly small. In a universe spanning 93 billion light-years, orbiting an average star among hundreds of billions in a galaxy that itself is one among trillions, the human species occupies no more space than a single dust mote in an endless cathedral of light. And yet, from this minuscule vantage, we have done something extraordinary. We have looked out and understood. We have seen galaxies forming at the dawn of time, mapped the invisible scaffolding of dark matter, measured the speed of cosmic expansion, and even peered into the event horizons of black holes. We have, in the most literal sense, made the universe conscious of itself. It is a humbling paradox. The universe is inconceivably vast, but it has also given rise to beings capable of conceiving of that vastness. Our telescopes are the eyes of the cosmos turned inward, our equations its thoughts taking shape. Every act of discovery, every photon we capture from the distant past, is the universe learning its own story. Through science, we are not merely observing creation, we are participating in it, carrying forward the same process of understanding and transformation that began with the first galaxies. When we look up at the night sky, we are seeing time itself, ancient light that began its journey long before Earth even existed. Every star, every faint glimmer of a distant galaxy is a message billions of years old, whispering, "This is where you came from." The light from Andromeda, our nearest galactic neighbor, left its home when early humans first began to dream. The light from the farthest galaxies left when the first atoms were forming. The cosmos is not just out there. It is within us, written into the particles that compose our bodies and the instincts that drive us to seek and to know. In contemplating galaxies, their birth, their collisions, their fiery lives and slow deaths, we are also contemplating our own. The same forces that shape them shape us. Gravity, time, entropy, and the ceaseless transformation of matter into meaning. Galaxies merge, stars are born and die, elements combine into molecules and molecules into life. Everything is connected, from the spinning of distant galaxies to the beating of a human heart. The universe is not a cold void, but a living continuum of energy and possibility, a tapestry woven from both chaos and order, both death and creation. And in that realization comes meaning. The galaxies will one day fade, the stars will die, and the universe will grow cold. But for now, for this brief cosmic instant, we are here. We are the witnesses of creation, like the chroniclers of light. We are the universe, for a little while looking back at itself with awe. The significance of that fact cannot be measured in years or in size, for meaning is not found in the scale of things, but in their capacity for awareness. To explore the galaxies is to expand not only our scientific understanding, but our sense of belonging. It is to recognize that the universe is not indifferent, because through us it feels. Through our questions and our wonder, it knows itself. The same curiosity that drives us to build telescopes and spacecraft is the echo of the same cosmic impulse that ignited the first stars, the drive toward illumination. In that sense, humanity's quest to understand the cosmos is not just an intellectual pursuit, it is an act of cosmic continuity. Perhaps that is the true message written in the light of every galaxy, that we are temporary but not meaningless, finite yet connected to the infinite. Our individual lives are fleeting, but collectively, through knowledge and imagination, we become part of something that endures far beyond our time. Every generation that looks upward carries forward the same flame, a light that began at the dawn of the universe and will continue to burn as long as there are minds to seek and eyes to see. So when you look into the night sky and see that faint milky band stretching across the darkness, know this: you are looking into your own ancestry. Those stars are your kin, those galaxies your heritage. You're not lost in the cosmos. You are the cosmos, conscious and alive for the briefest moment, yet part of an unbroken chain that stretches from the first atoms to the furthest galaxies. And in that realization, in that quiet, humbling awe, the journey comes full circle. The galaxies we have traversed, from the nearest spirals to the faintest lights at the edge of time, remind us that our smallness is not insignificance. We are part of something greater than we can ever comprehend. And it is enough simply to wonder, because in the end, to explore the galaxies is to explore ourselves. To look outward into infinity and find, reflected in its vast and silent depths, the enduring light of our own consciousness. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.